Alright, so yesterday we finished partial and semi-partial correlation. There's one more thing left in there, but I'm gonna cover them while we talk about multiple regression later.
Okay.
Alright, so that will be E.
We're gonna do it.
Yeah, because correlation is D, I believe. This is multiple regression. And on the packet, the pages are 63 to 65, 67, 69 to 72, and 73 to 74. They kind of like put a multiple regression everywhere. I also mixed them up with the path analysis and structural Gaussian modeling. So even though they're on those pages, but you just filter out the contents that I'm going to talk about like right now.
Okay.
So when you read through pages, you may find some of the contents are not matching with multiple regression because they're not really quite following the multiple regression. So first of all, multiple regression is actually an extension of correlation. Because remember, when you do correlation, you're studying association. You're looking at if variable A is correlated with B, or the other way around, whether the variable B is associated with variable A. So that is correlation. So when we do regression, it's actually we're building a causal model. Yeah. So we're trying to create a causality between the variables. So we're not just focusing on correlation or association. We're looking at causality. We're trying to looking for whether certain predictors, for example, like A, is going to cause an outcome, which is B. So here is the cause.
Okay.
Yeah. So that's why it's beyond the analysis or what the correlation is going to do. Because right now we're causing something. We're trying to predict the future. Yeah.
That could be very beneficial.
Yep, exactly.
So in a correlation, there's no cause.
Yeah, there's no causality. But when you do regression, you're trying to predict. So even though you don't have a data, if you have a predictor's value, by doing a regression analysis, you find out what's the relationship between them. So with every given value of a predictor, you can find out the outcome or the results of the outcome, the B, the variable B.
Okay.
Yeah, so that's what multiple regression is good at, or that's the purpose of doing a multiple regression, which is discussed on page 63. Yeah, they talk about why we do multiple regression and what is the benefits of doing a multiple regression over correlation.
Page 63?
Yeah, 63. That's the definition, which I just described. So the first thing, so what I'm going to call it is, so that's the differences from correlation. Yeah, because sometimes students got confused. They don't know, like, what's the difference between correlation and regression? They sound it's the same thing, but it's totally different. And of course, mathematically, they're similar because they're all looking for coefficients, like how two things are related. But just regression on the more theoretical way is much better than correlation because you can predict. So the second under the multiple regression is we have to find out what's the structure or components of doing a multiple regression. So here we're not going to talk about IVDV, right? Because remember, like I said, IVDV is only for t-test, ANOVA, MANOVAs. So in the multiple regression, we're going to call predictor and cause the outcome.
Can you have multiple predictors?
Yes, definitely. Put a little S here. So you always have one outcome, okay? So this one is like, yeah, it's like in ANOVA, you always have one DV. So in multiple regression, you always just have one outcome. And sometimes we call predictor a explanatory variable. And outcome, sometimes we call it a criterion, which already discussed on Friday. Explore all the definition of variables. And technically, for both of these variables, they all have to be continuous or ratio. So you cannot have a categorical.
What's a ratio?
Ratio means you measure it by numbers, remember? 'Cause we have 4 types of measurement of variable. There's a nominal, categorical, ordinal, interval, and a ratio. So ratio is like a scale continuous variable. So you measure the variables by numbers. And those numbers has meanings and differences. So that's like a basic structure of multiple regression. And the next we're going to talk about the assumptions required in multiple regression. I hope you still remember the assumptions required for audio analysis we discussed 2 days ago. No, sorry, yesterday and the day before. So for multiple regression, the first one is normality. And here they have some little bit difference, because if you notice the variables that included in multiple regression, both of the variables, they are all ratio and continuous.
Yeah.
So which means they're different than t-test or ANOVA or MANOVA, because in t-test, the IVs, they're categorical. Only DV is continuous. So when we check normality for t-test, ANOVA, and MANOVAs, we only check for DV's distribution, right? To see whether they're normally distributed. But here, here is actually we also need to check predictors.
Okay.
So that's why when we check the normality in multiple regression, we're actually checking the multivariate normality.
That just means multiple variables, but.
Yes, so multivariate here doesn't mean multiple DV. It just means the multiple variables, because both predictors and outcome in the multiple regression, they're all continuous. Yeah.
Okay.
And to check this assumption, we need to use Mahalanobis. Oh, actually, yeah. For the Mahalanobis distance.
That's the test?
Yeah, that's the test. To run it to check whether we satisfy the multivariate normality. Because remember in t-test, ANOVA, MANOVAs, or correlation, we do a normality test, that Shapiro-Wilk test, to see if the p-level is bigger than 0.05. So Mahalanobis, they don't have a significance. What you do is that you compare the calculated Mahalanobis distance for your variables, and then you compare that with the critical Mahalanobis, and you can see if your value is bigger than or smaller than that critical. If it's bigger than the critical, that means you do have, violate the assumption of normality. So which means actually you have outliers. So you need to delete the outliers to achieve multivariate normality. But if your calculated Mahalanobis distance is smaller than critical, then you're good.
You want smaller.
Yeah, you want like smaller than critical. Yeah, they don't have like a significant testing.
Okay.
Yeah, you just do a comparison with the critical value. You need to be smaller than that. Next assumption for multiple regression is independence of observation, like the assumptions we discussed for t-test, ANOVA, MANOVA. So your individuals or subjects has to be independent from each other. So which means they don't influence each other, don't talk with each other about the research. Following one is independence of error. So in regression is actually we also need to check the independence of error. So actually error here, we can also call it a different name. It's also called the residuals. So what caused these residuals? Because remember, right now we're trying to predict the outcome, right? So we're going to analyze the data that we collected, which is a sample. So which means whatever we calculated, we have like the sample data, which is the observed, the actual value. But because multiple regression has a function, they're predicting the future. So which means even though you don't have that certain number or certain data in your current sample, you can still predict with like a fake number, right? With a given number, you can like calculate what's the outcome would be. So because of that function, we're gonna create a residuals because there's gonna be a difference between the observed or the actual value with the predicted value. So that's where the residuals comes from.
So not too much of a gap, basically.
No, it doesn't mean it's the gap. I'm not
Okay.
saying residuals bigger is good. Of course, you want it smaller.
Yeah.
That's the difference. Yeah, the gap between the observed and actual value.
Is that like variance that's not accounted for by your predictors?
Actually, yeah, you can say that, but yeah, that's right. That's also you can say it's the unexplained variance.
Okay.
But remember, when we talk about the variance, we're talking about the whole model. But
Mhm.
residuals is coming from each of the data. Yeah, variance is like for the whole data. So let's just say if you have like 250 peoples, remember you talk about their total variance to explain the your outcome.
Mhm.
But when I talk about residual, I'm talking about each of these 205 people.
So it just
They all
means
have a residual. Yeah.
so it just means that your predictors are relatively clean. There's not a lot of
Not too clean, which means that they're better predicting, the data or the model that you
Yeah.
just built up. Yeah. So that's why independence of errors, which means each of that individual's residuals, they have to be independent from each other. So their errors also has not to be correlated.
okay.
Because remember, the observation is for the actual data, but residuals is the difference between the actual data and the predicted data. So that means this gap also has to be independent from each other.
Okay. So all the individual error for each person would be independent of each other.
Yes, exactly.
Perfect.
And to check this, we do have a test. It's called Durbin-Watson. You should remember that, or I don't know if you remember that. It's called Durbin-Watson test. And I think in Dr. Gewert's class, it's supposed to be like bigger than 2. To make sure that you didn't violate the independence of error, the Durbin-Watson needs to be bigger than 2. But Richard had like kind of different suggestion because he looked up online and he find out some studies saying bigger than 1.5 is enough. Some say that it should be like less than. Oh, actually it's not. It's supposed to be like
Equal to 2?
yeah, like similar to 2, like close to 2. It could be like a little bit bigger or smaller. Yeah. Sorry, not bigger than 2. Yeah, but Richard finds some different things because I just want to mention that out just in case if you guys looking through Richard's Hawk, video stuff. Yeah, he has a different range.
Okay.
Yeah, but Dr. Gewertz, like he goes for 2. And the next assumption is homoscedasticity.
I remember that.
I know. Make sure you can write the word right. So this one, the opposite word for homoscedasticity is heteroscedasticity.
Mm-hmm.
Yeah, because the com may write 2 words.
So they're opposites.
Yeah, they're opposite.
Okay.
And we want homoscedasticity. We don't want heteroscedasticity.
Okay.
Yeah. This assumption actually means that whether these residuals, they are evenly distributed. Yeah, that's this assumption means.
What are evenly distributed?
The residuals of each subject in your data, whether they're evenly distributed. Yeah. So which means, because they actually, in the SPSS, they draw a plot. So this is the residual actually.
And what does residual mean? It's like error?
Yeah, it's like error between the observed and predicted value for each subject.
Okay.
Yeah. So they have like a residual of 0, right? And they have -1, -2, because they're all, plus these are standardized residual. Because if it's standardized, it's like a z-score. So you only have like a 0, 1, 2. So they have +1, +2. So like they draw this line here, and then this is all your residuals of your data. So which means is that you want like the residuals below the 0 and above the 0 are equal, like pretty much the same. So when you add them up, they're going to be equal to 0, right? That means you don't really have a residual.
Yeah.
So this is what homoscedasticity means. They're evenly distributed.
Okay, that makes sense.
Yeah.
So you don't want all the air on the top or all the air on the bottom. You want it equal.
Yeah, like for example, if your charge, if I draw it like this, yeah, that's the heteroscedasticity.
Yeah, 'cause
See,
all
you have
above
more
one.
errors
It's
on the
different,
above
yeah.
the other. Yeah, you have less error under the 0. So that means you have more positive error over like negative error. So this one you're definitely gonna have heteroscedasticity issue.
Okay.
So yeah, so to check this assumption, usually we just draw this plot. There's no task, or anything.
Okay.
Yeah.
That just be a scatter plot?
It's not really a scatter plot. It's called a residual plot.
Residual plot?
Yeah.
Okay.
But I don't think a comp's gonna ask you that. Yeah, you just need to know this assumption and what does the assumption mean. Yeah,
Okay.
they're not gonna ask you how to check it.
Helps for dissertation.
That's true.
I'm using regression.
Oh, you are?
And over.
Mm.
Yeah, when you do a dissertation, I'm not saying you have to go fancy analysis. Just go basic, easy ones. You can get it down.
Degree.
Yeah, you can get it down ASAP. Yeah, don't
That's
go
great
complicated.
advice. I will take that advice.
Good. Okay, so actually sorry I have to change the marker because that line's dying. So next assumption for regression is linearity. And to check this one is we use a scatter plot. And this is similar to the linearity we talk about under correlation. So you just have to make sure each of your predictor has a linear relationship with the outcome. Yeah, remember we talk about linear?
Yeah.
It's like this. So cannot be like this, cannot be like this, cannot be like this,
Yep.
and cannot be like this.
Okay.
Well,
Yeah.
that's
No
predictable.
squiggly and no flat lines.
Yeah, so make sure it's linear. Yeah, this is called
Got
number
a,
reading.
Has
gotta
that
have
a
a
slope?
slope.
Yep.
Okay.
Yeah,
You got it.
yeah, this is slope.
Those are also just an inconsistent predictor.
So if you, let's just say if you have a 3 predictors.
Inconsistent?
Yeah, without being linear, what would be inconsistent?
So if you have multiple predictor, each of the predictor has to have a linear relationship with the outcome. Yeah. Otherwise, they're not going to even include that predictor in the analysis. So last assumption is multicollinearity.
A lot of assumptions.
I know, yeah. Pretty much the more advanced the statistic is, the more assumptions will be required.
Yeah.
Because remember, statisticians are using more complicated mathematical formulas to calculate, stats for you. That's why their data has to be, can best, analyzing the model that you're building. So that's why regression is a very complicated, stats model. That's why it requires more requirement for data. Yeah, because if you look at this, it's all pretty much make sure you have a good set of data. So when you analyze it, you can have a really, closing to the true results, findings. So multicollinearity, actually, the interesting that this is the only assumption that we don't want, right? Because look how we want normality, we want this, we want this, we want that, we want that, but this is the only assumption that we don't want.
Okay.
Yeah, so that's the only special case. Yeah, every time we talk about assumptions, we always want those assumptions, right? Yeah, so this is the only assumption and only in multiple regression that we don't want these assumptions.
So this is where we want p below.
Multicollinearity.
Yeah, plus, no, this one has no p, but you don't want multicollinearity.
Okay.
Yeah.
Okay.
Yeah. First of all, I will explain what is multicollinearity means. This only happens when you have more than one predictor. If you have one predictor, actually, you don't have this issue because it's multi, right? So when you have more than one predictors, and if your predictors are extremely highly correlated, which means you cannot tell which one is which one, which means they actually explaining the very similar results on outcome. That means multicollinearity, because you cannot tell the difference between the different predictors. It's kind of like they're overlapping. So let's say if you have 2 predictors, they're pretty much they're like the same circle. Yeah,
Okay.
they're overlapping too heavily. So when you have a DV, you cannot tell how much variances these predictors explaining and how much variances these predictors explaining, because they're overlapping too much.
Okay.
So that is multicollinearity means, and we don't want it.
So it's too much overlap.
Yes, exactly, between the predictors. Yeah.
Okay.
So to check this is actually we're using what we call the tolerance or VIF. I think they have the whole name for VIF, but I always call it its abbreviation. I rarely remember
What do you call it?
VIF, but they have like a whole name.
Okay.
Look for it. It's on page 73. Yeah. Let me see. Huh, they didn't say it. That's interesting. But I see it on the packet somewhere. So probably it's in the other pages. Yeah, you're gonna find it. Because actually they mean the same thing. Tolerance mathematically equals to the they're inversely related. So tolerance equal to 1 over VIF. I think this one is a variance in inflation. Kind of. I forgot. I'm sorry. Yeah. Because on the comm, students said that they saw questions asking about how to check multicollinearity. Yeah.
So you just say you use
Tolerance or VIF because they are the same thing. Yeah. This one is just the other one inversely related.
okay.
So therefore, when we check this, the tolerance has to be less than, has to be bigger than 0.1, where VIF is less than 10, to make sure that you don't have multicollinearity.
So we want tolerance bigger than 0.1.
Yeah, so tolerance has to be bigger than 0.1, or VIF is less than 10, means that you don't have multicollinearity.
Okay.
Yeah,
Okay.
which means if your tolerance is less than 0.1, or the same thing, if you look at a VIF, it's definitely going to be bigger than 10. In that case, you have multicollinearity, which is not good. Yeah, that means your two predictors were like a few of predictors. They're highly overlapped.
Yeah.
Yeah, you're not going to be able to tell the difference how they uniquely explain the variance of the DB.
Okay.
Yeah.
Makes sense.
So these are all the crazy assumptions required in regression.
Right? 1, 2, 3,
Yeah.
4, 5, 6.
The good thing is that in the column it's all multiple choice, but when if you're going to do a regression in your dissertation, you have to discuss them all.
Yeah.
Oh wow.
Yeah.
Oh wow.
I know. Yeah.
Do you have to discuss every assumption for every
Yeah.
statistic in your dissertation?
Yeah, you should technically.
Wow.
Yeah. Because remember, if your data is not satisfied with the assumptions, technically you cannot proceed with the analysis. Yeah.
Right.
But like, of course, every time, remember that fancy name we call robust?
Yeah.
So your regression actually robust also applies. You can easily say, oh, for example, let's say if you violate this assumption, because some of the assumptions like this one and this one, it's very hard to, correcting them. It's not like say you do something on your data, you can change this thing.
Yeah.
Which ones are hard to correct? The
Like,
independence
yeah,
and
because
errors?
they're the residual. You cannot really adjust it, right? Yeah. Because you first of all, you don't know what's the predicted value. Whatever you have is just the actual value. That's why you really have a minimum control over this distance or gap between the observed and the predicted. Plus, yeah, homoscedasticity is also about error, residuals, right? So it's really hard to control these two. So that's why whatever data you have is just whatever data you have.
Right.
It's not really something you can do really about it.
Yeah.
Yeah, so most of the time, as long as they're not that severely violated, we just say, yeah, they're still minorly violated, but we just say, okay, because it's robust, so we just continue doing the regression.
Which one's most robust?
No, we just say,
They're all robust.
yeah, like they pretty much regression. No, every time we say robust, we talk about the analysis.
Okay.
You're just gonna say the analysis is robust.
Okay.
Therefore, even though the assumptions, some of them are violated, you can still go ahead, yeah, with the analysis. Alright, so that's assumptions, and the next we're going to talk about the key part or components of regression. So let's start with the type. So when we do multiple regression, there's a bunch of different ways to do it, so that's a type. So the first one is called simultaneous multiple regression, or you can call it standard multiple regression.
So these are all types of multiple regression.
Yeah, like a different procedure to conduct them
Okay.
after you check your assumptions. Yeah.
Okay.
I can't write English today.
You spell better than I do.
Okay.
No, seriously, you do.
I wish I could write Chinese. I don't even know how to write Chinese. I don't know Chinese about stats. Oh, because I learned stats in
In
English.
English.
Which is really funny. Okay, so next one is hierarchical question. The last one is a stepwise regression. So all the types are described on page 63. So pretty much these are the three most common types of regression that we usually run for not only for dissertation, if you do research, you can end up doing these three different types. So the first one is simultaneous. That means if you have, if you have like a predictor 1, predictor 2, and a predictor 3, you're going to use them to determine one outcome. So to do a simultaneous is we put all these predictors into the regression model at once.
At the same time, simultaneously.
Exactly.
Okay.
That's why it's also called a standard regression.
Oh, it's okay.
Yeah, you can call standard because sometimes they say it's a standard regression. Yeah, sometimes they say it's simultaneous, but they mean the same thing.
Okay.
So this is how you do a simultaneous. So you pretty much introduce all the predictors all at once together to see what is the predictions of each of those predictors to the outcome. The second type is hierarchical. So hierarchical is like this. You still have like multiple predictors, okay?
Mm-hmm.
And then you're gonna define what is the order of how you enter the predictor into the regression model. So actually you do them step by step. So you analyze predictors one at a time. Yeah, you're not analyzing them all at once. Yeah, you're analyzing them all at a time, and based on the order that you give it to the predictor.
Okay, so you choose the order.
Exactly, and that's based on the research, and then you choose the order pretty much, based on literature review or theoretical reason. Yeah.
Okay.
So that's how you do hierarchical regression. And the last one is a stepwise. So the same thing, when you have multiple predictors, you let the computer, which is actually SPSS, to choose the order of how to enter, each of the predictor at one time to predicting the outcome. So this is going to be SPSS job, but it's the same thing with hierarchical. The similarity between hierarchical and stepwise is you all enter the predictors one at a time. It just hierarchical is you choose the order, and stepwise you let SPSS choose the order. So that's why this one is more based on mathematics. It's not really, based on
conceptual.
Yeah, exactly. It's purely just computer determined order based on like the math. So that's why usually, if you want to do this, like usually we do the hierarchical first. Yeah, to like theoretically to filter out, which predictors supposed, to be the ones to be entered into the model. So because when you enter them step by step, you're going to filter out and find out, where is the model I should stop, which means with further predictors added, the model not going to be improved. So you can filter out which of the final, for example, if you do this, it's possibly you're going to, remove predictor 3. Because after you enter them like each by each, you find out after you enter predictor 3, the model variance, which is, R-square I'm going to talk about later, not going to be changed that much.
Mm-hmm.
So which means that predictor 3 is not going to contribute much to predicting the outcome. So that's why, for example, if you do hierarchical, you say, okay, theoretically, I should just stop at adding predictor 2. Yeah. And then after that, you can maybe let the computer do a stepwise to find out which of these two predictors has the highest contribution on the outcome.
So when people do multiple regression statistics, do they normally do all 3 of these?
I don't know. You can choose either one of them.
Okay.
Yeah, but
Can
sometimes
you do all 3?
you can do that. Yeah.
Is it a waste of time normally, or?
No, it depends on how you do your research design. Yeah, like I said, if you let's just say if you have like a 15 predictor, right? Technically, you can run a simultaneous, but you see, it's just gonna be you put them all together at once. You cannot tell which one is the strongest predictor, or which one is the weakest, or which one is not even predicting. You don't know that by doing a simultaneous.
It would just say like out of these 15 predictors, they predict 70% of the variance.
Yeah, and
That's
then
all I'll tell you.
Yeah, and you cannot tell which predictor is highly predicting, which predictor maybe you shouldn't waste that much to study on it, right? So that's why You can choose to do a hierarchical as a follow-up or stepwise as a follow-up, conceptually and mathematically to filtering out and to remember, because the point is to build up the best fit model. Yeah, because we're trying to have the best fit model.
Big model?
Yeah, we call it like a best fit.
Oh, best fit. Okay.
Yeah, because remember you always want
Yeah.
the best fit, the most accurate or perfect model. Yeah, even though it's not going to be perfect, but that's our purpose. So that's why you can do this to filter out all of the 15 predictors. Maybe I just need 5 of them, right? Because these 5 of them, they're highly contributing or explaining the outcome, and that's my best fit model.
Okay.
Yeah, because this is more like, related to, practical significance. Because remember, we're humans, right? We don't have that much of time or effort to really, focusing on all the 15 factors. So that's why we're trying our best to, eliminate, the efforts or the work we need to do to trying to reach the best results, right? That's what efficiency lies on. Yeah. So that's why, when you do hierarchical and stepwise, they can give you a better, results
better idea
compared to
than
simultaneous.
Okay.
But of course, if you just have a few, predictors and simultaneous, if it's enough for you, then you can just do it. Because compared to this one, simultaneous is kind of like the easiest type of regression.
Yeah.
Yeah, because you just
Simple.
pull them all at once, yeah, and you get the results. Yeah.
Okay.
Okay. And one more thing is stepwise. The SPSS, they do like a kind of like a different, procedure. Of course, that's SPSS job. They can do like a forward, backward. Pretty much SPSS either like arranging the order of the predictors from the weakest to the strongest, that will be like forward. And if they're doing from the weakest to strongest is backward. But if they do from the strongest to weakest, that is a forward.
Okay.
Yeah, but that's SPSS thing. You don't really have to worry about that. Yeah, but in hierarchical, usually we do like, from the strongest predictor to the, the weakest. That's the type. Next, we're going to talk about the key components of regression, analysis results. Or when you do have a result of multiple regression, how you should, interpret or talk about them. This one is called line of best fit. It's also on page 63. So line of best fit is actually going to help you to create your predicted regression line. And to draw a graph is going to help you understand the idea easier. So this is our outcome. That's the predictor. Okay, so let's just say we have like a bunch of the data collected, and then we pull them up on the like a scatter plot. Right. So the line of best fit is pretty much the SPSS or the program, or if you do like a by hand calculation. So this line of best fit is also called like a predicted line or regression line. So we're trying to use the actual data to predict if we have this along able to be extended infinitely, what's the possible line should be look like, or where it's supposed to be lined up. Because remember, every value on the line is a predicted value, because each dot is our actual observed. But on the line, the dots, they're predicted, which means they probably not the data, that we collected. I mean, some of the data could be falling on the line, but not all of them, because this is the predicted line that we're trying to get out. Yeah. So that's what line of best fit means. So to get this line is actually we're trying to calculate each of the score, that's the observed, right? To the predicted line, make sure they're
not too far away.
Yeah, first of all, not too far away is actually, even though they're too far away, but also we're trying to make sure that these, residuals is gonna be able to be offset to 0.
It's similar above and below.
Yeah, exactly. Similar or equivalent. Doesn't have to be exactly the same, but we're trying. So that gives us,
possible.
that is how we draw out the line of best fit line, and also we also call it a regression line or predicted line.
Okay, that makes sense.
That is the actually, we can say the mathematical reason. That is the mathematical base of regression, multiple regression.
Yeah, regression's my favorite of all the stat stuff.
Yeah, it doesn't have any stats reason. It's just a mathematical reason.
Yeah.
So we're trying to reduce the error or the mistake or the residual.
It makes the most sense to me.
What's that?
Another ghost.
Ghost is Wuxin. Wujia.
What?
How do you say ghost?
Way.
Wei.
Yeah.
That means something very different in Spanish.
How do you say in Spanish?
Way?
How do you say ghost in Spanish?
I don't know.
Why you know it's different in Spanish?
Way?
Way.
Oh, Gway. No,
Yeah.
never mind. Okay, so Gway.
Yeah.
Way is a bad word in Spanish.
Oh.
Mm-hmm.
Okay. Yeah, it's not way. It's way.
Yeah.
It's different.
This ghost?
Yeah, it's ghost.
I thought ghost was like Wujia. No.
No.
Sounds like Ouija board.
Yeah.
Maybe I should talk actually the next components, but because the packet is put like together with those key components, so I don't feel like it makes sense to me. But yeah, I'll put it here. So it says like a simple regression on page 64. So actually, simple regression it just means that you only have one predictor and one outcome. That's it. That is what simple regression means.
Okay.
Yeah. So you see, technically, we should talk about simple regression before the multiple regression. But they didn't really discuss much about this. They put it under with those key components. Yeah. So you just need to know, if you say simple regression, in the columns that regression you only have one predictor.
Okay.
Yeah, and of course one outcome. Yeah, that's why multiple means that you have multiple predictors. And because from the simple regression, that's how we're introduced to the regression equation. So that's the next components.
Regression equation?
Yeah. Remember, every time you run the multiple regression, remember we're trying to predict the future. So you should be able to come up like an equation to be able to predict. Yeah. So that means with every given predictor value, you can have a predicted outcome calculated. So it's like this, and on the packet, I don't know if they don't know how to draw this thing in a Word document, because if you look at page 64, this is called the predicted y, right? Because it's not actual y, so you have to put a little cap on it. But on the packet, they put like this. I have no idea why they do that.
So you can figure out how to type it.
Yeah, I don't think they know how to do this, but they can do this in Word. I mean, someone they probably doesn't know it. It's back in 2007 when packet was made, so. Yeah, that person probably doesn't really know how to do Word. Or Word is not that fancy back then. I don't know. Yeah.
Word is always fancy.
So this is the basic regression equation. Yeah, of a regression formula when you write it up. So this is the predicted y, and the little a here is intercept. And sometimes we also call it constant. And the b here is actually the unstandardized coefficient, or you can call it b weights.
This is just the.
Yeah, sometimes you can call it b weights. Because b weights is how the SPSS draw it up. And x here is your predictor. Remember, we're still following the simple regression because we came up the regression equation based on the simple regression. So if you have a simple regression, this is how you write up a regression equation. And if you have like a multiple regression is supposed to be like this. So it's a plus b1 x1 plus b2 x2 plus bn xn, and then depending on how many predictors you have.
So x is the predictor?
Yeah. And this just means you have predictor 1, 2, 3, 4, blah, blah, and predictors.
So b1 x1, b2 x2.
Yeah. But the same thing, a is still your intercept or constant. This is the unstandardized coefficient for predictor 1. This is the unstandardized coefficient for predictor 2, and blah, blah, etc., etc.
And in every mix, you never have like b1 x3.
No.
No?
No.
Okay.
Remember, that's the coefficient corresponding to each of the predictors.
So they always are paired up.
Yeah, they always
Okay.
paired up. Yeah. So this is just for a simple regression. That's for like a regular multiple regression.
Okay.
Yeah, because they drag this coming like derived from here. That's why they always introduce simple regression first. And on the packet, they kind of like saying that this is also the unstandardized regression equation because you use the unstandardized coefficient. So they actually also transform it into a standardized.
So this equation you give us is the standardized or unstandardized?
Yeah, this one is like unstandardized.
Okay.
Yeah, and then from here they transform it into the standardized regression equation, which is there's going to be no constant. So if it's a simple regression, you just have like a big B and X. Yeah.
Okay.
So this is going to be standardized coefficient, and you don't have the actual intercept anymore.
So the one on the left would be like a multiple regression.
Yeah,
And
so
one on the right would be a
this is for simple. Yeah, so if you transform this one to a standardized regression equation, it's going to be y equals big B1 x1 plus big B2 x2.
So what would that be considered? That would be the standardized version of a multiple regression.
Yes, that's right.
Okay.
Yeah, I've never really read these regression out. I never even seen it in any articles or dissertation. But the packet put it up, so that's why I just put it there. But these two are really, really used because the standardized coefficient doesn't mean anything. Because when you standardize it up, you cannot tell if every unit of predictor change, how much unit gonna be the outcome change. Yeah, because they're standardized up. They're like a standard deviation change. But this one is like, for example, let's say if our predictor is age and the outcome is income, so you can tell with 1 year's add up, you can have how many income increased. But if you do this, you cannot tell that. You cannot say that because they're standardized score. Yeah, they're not like the actual raw score of the data. Yeah, this one we can even tell between the age of 25, for example, 26, if we find out the regression equation line for the study, we can find, okay, with a different age of people, how much income they can make. But if you do a standardized, regression equation, you cannot find out anything because the scores are standardized. Right. It's not the original raw score, yeah, between age and income. Okay. Yeah. So that's why practically this regression equation doesn't make any practical sense. Yeah, that's why I never seen them discussed or described or written out in a dissertation or article, but just because the packet talk about it. Yeah. So yeah. Okay. So that's why they also say the unstandardized is like the raw weights or the raw coefficient, because they're the original score of the predictor and outcome. Okay. Windows 5. I'll just put back here. So the next one is we're going to talk about R square and adjusted R square. Okay, so this is like the next important components of when you talk about results of regression. So R, remember we talk about under correlation that is multiple correlation, but usually remember because regression is like an an extension and a better estimation beyond correlation.
Mhm.
Usually we don't really talk about R in regression, even though SPSS created. Most important thing is R squared and adjusted R squared. So R squared is also called coefficient of determination. So this one explained how much variance of your outcome can be explained by the predictors. So if you're gonna remember, draw that correlation thing. I'll just make it simple. So let's just say this is our outcome, and this is the predictor. So if we draw this like shadowed or overlapping part, this is gonna be your R squared. Actually, this part is gonna be residuals. They're the unexplained variance. So this is the variance that actually we can have the predictors explained to the outcome, or like the part that outcome can be accounted for from the predictors. So let's just say if you have remember multiple predictors, remember the partial and semi-partial withdrawal yesterday, so we can make it a little bit complicated. So let's just say we have 3 predictors, then the R square gonna be like this.
Okay.
Yeah. So you see, with more predictors, you can explain more variance, right?
So
Because apparently the shadow part is actually bigger than
R squared is going to be that in all the shadow.
Yeah.
All 3 is R squared.
Yeah. So all together, they're all R squared. Because remember, when you talk about R squared, you always say the total variance of the outcome can be explained. Yeah. Because you're not discussing each of the predictors, variance explained. You're talking about total variance. Yeah. That's why it's all the shadow part that these 3 circles overlapped with.
So it's the total variance explained.
Yeah. Mm-hmm. Yeah, so that's why you see, the less predictor you have, the less, of course, that R square going to be. The more predictor you have, the stronger R square will become. That's
Both
why.
examples, the top part is the residual.
Yeah. So apparently, yeah. For this case, yeah, this is going to be the residual. So whatever that outcome cannot be shadowed or overlapped by the predictor is going to be the residuals. Yeah.
Okay. And when you call the white part of the empty part of the bottom 3 circles.
Yeah, these 3 we don't care, because remember, you just care about.
So we
outcome.
don't even have a name for it.
Because we don't care if predictors have anything unexplained. We only care about the outcome.
Cool.
So that's a little bit different than correlation, because in correlation we look at both, left part. But when we do regression, we only care about the outcome. Yeah.
Okay.
We don't really care about if these parts of the predictors can be explained or not, because they are not our concern. Yeah.
In correlation, because I think that was the part that I missed yesterday, is that with the partials and the semi-partials?
Yeah, when we draw this, we do the partial and semi-partial.
Do they have that with multi-regression?
Yeah, we do.
As well?
Yeah,
Okay.
I'm going to calculate it. Yeah.
All right.
Is your person stuff safe in the background? With people coming in or out?
Oh no, it's fine.
Okay, I'm just making sure.
You don't have any money anyway, huh? That's what I.
Oh no, usually they don't really go to
Okay.
different places. Yeah, so that's why we know the R square here, because remember when we talk about effect size in ANOVA? Yeah, so that's why R square is also the effect size, because you're trying to just explain how big the outcome can be explained by the predictors. Yeah.
Okay.
So that's why we also call R square is the effect size, and if you calculate R square, you can talk about how much variance can be explained by DV, which is also the effect size. It's like the same thing. So next one is an adjusted R square. So the interesting is that these 2 are like the same thing. This one is actually also a coefficient of determination. Actually, adjusted means that they adjusted the error. So let's draw this. I'll just use the 2 of them. 3 is fine. Remember when we talk about R square, it's this part and this middle part and this part like together. No, I'm gonna use different color. Yeah, so this is original R square, right? Like we talked about earlier. So adjusted R square is like Because remember, it's actually this part you've been overlapping twice, right? Because variable, like let's just say this is predictor 1, predictor 2, and that's our outcome. So like this little predictor, when we overlap with the outcome, they already take count of this. But then you have predictor 2 do it again, right? So actually this part has been doubled like twice.
Right.
So what adjusted R-square is doing is actually they take out like the additional overlapping part.
Completely remove it?
Not
or separate it?
Yeah, they don't remove like predictor 2, but they just take off like, because this part has been overlapped twice.
So it doesn't really.
Yeah, so technically we should take them out, right? To give what's the accurate prediction on the outcome. Yeah, so that's what adjusted R-square does.
Okay.
Yeah, it still have all the 3 part, except that for this part, adjusted R-square is better predicting Y. Instead of, R-square actually counted as twice. Like it counted like from predictor X1 and also from predictor X2. So R-square do it twice. So actually it's redundant.
So adjusted R-square doubling does it once or doesn't do it at all?
Yeah, R-square does it like twice. Like
No, adjusted R-square.
Oh, adjusted R-square like make sure that you purified. It's actually purified this little
So
section.
is it gone?
Yeah, did they remove it completely
No,
or
they didn't remove it. They still
clean
keep
it up?
But they just count it once?
Yeah, they only count it once.
Oh, they count it once. Okay.
Yeah. So that's why adjusted R-square. So that's why we always say adjusted R-square is a better prediction. So this one is always smaller than R-square.
And why'd you write effect size up there?
Because R-square is effect size, remember? Yeah.
R-squared is the effect size.
Yeah. Remember when we talk about effect size, we have 3 different effect size, eta squared, R squared, and omega squared.
Yeah.
And I said I'm going to talk about again and regression. Yeah.
Okay.
But it's part of the effect size section.
So adjusted R-square is also a measure of effect size.
Yeah, exactly.
Derek, I'm glad you asked that question.
So that's why mathematically this one is always smaller, because we're taking out of the redundant part. And adjusted R-square better with a smaller sample size. So with the bigger sample size you have, the differences between the adjusted R-square and R-square is harder to be discovered. But with a smaller sample size, because when you redundant up, you can easily find out difference.
Okay.
So this is better.
Prefer a
It's
smaller
better.
sample.
Yeah. So if you have a smaller sample size, it's better to report an adjusted R-square over R-square. But if you have like a large sample size, you can report both. And most of the case, we just report R-square. Yeah.
Okay.
Before we go ahead, so far any questions? Just want to make
Not
sure.
yet. Okay.
Next, we're going to talk about the regression weights. So regression weights is for each predictor. So each of your predictor, in your regression model, have to have a regression weight to explain the outcome. And if you do a SPSS, or do a statistical analysis, you know that a significant predictor is going to have a significant regression weight, so which means P needs to be less than 0.05. And if the P is not less than 0.05, you find out there is a regression weight, but if it's not significant, you're still not going to include that predictor in your regression model. So in regression weight, we have 2 types. The first one is the unstandardized regression weight, which we talked about earlier under the regression equation. It's also called unstandardized coefficient. It's the same thing. And of course, the other one is standardized. So we use the letter B to represent unstandardized regression weight, and we use the letter actually beta. Probably. Actually, don't write out the Greek letter beta, because that will be confused with type 2 error, right? Because remember, type 2 error is beta. But still, we call this one beta, but when you write it out, you write out like the whole
word.
Yeah, whole word.
Okay.
Yeah, don't write out that letter, because that's gonna confuse with the type 2 letter. So we're comparing actually the standardized regression weights of each of the predictor to find out which one has the strongest, contribution on the outcome, which one has the smallest, or which one has the moderate. And here you can understand the standardized coefficient regression weight as the correlation coefficient between your predictor and outcome.
I don't understand what that means.
That means they serve the same function. Because remember, when you talk about the correlation between variables, you use the Pearson correlation coefficient, right?
Mm-hmm.
That's little small r.
Yeah.
So actually, standardized regression weight is like the small r.
Okay.
Yeah. So they're talking about what's the correlations, or how much correlation that can relate it from each of the predictor to your outcome.
Okay.
So that's why this value will really talk about like how much variance can be explained, because that's just the correlation coefficient, right? That's not variance. That's why we only use the standardized regression weights to compare the contribution of each of the predictor to see which predictor is the strongest predictor, which predictor is a stronger, and then you just compare the order to see which predictor is better, which predictor is not that better.
So we mainly use beta, and we standardize it when we're trying to compare the different predictors?
Yeah, and because remember, they're not explaining the variance, because students got confused. They thought, oh, we use this to explain how much variance that each predictor explained on the outcome. That's not, because remember, like I said, it's like small r. Small r is not variance. When you square it, that's the variance. Yeah, so don't use the standardized regression weights to explain how much variance can be explained from each of the predictor to the outcome.
Kind of following you.
No, because when you learn regression, remember, you have to talk about standardized regression weight. But remember, you always say how much variance can be explained.
Mm-hmm.
So this is not r, okay? It's not r here.
It's r squared.
Yeah, and remember, r squared is for all of them.
Yeah.
Yeah, but again, we don't say these as r squared, because when we say r squared, we mean the big R squared. We never really square the little r. Yeah.
Okay.
So what is the little r?
Pearson correlation.
Yeah, the correlation coefficient, but in regression, they're called a standardized regression weight. Yeah. I'm just saying they are serving the same function.
So the beta is
They're
the
different. They're
standardized
different things, but they're doing exactly the same job.
So it's what each predictor contributes.
Yeah, they're talking about, no, they're comparing which predictor is better, which
Okay.
predictor is not that better. Yeah, so they made it, because remember, when you have multiple predictors, you have to say which predictor is better, right? Yeah.
Yeah.
To be able to tell like how much efforts we're gonna trying to improve the subject's outcome by working on certain predictors who are best predicting the outcome. Because we're not gonna waste the time to focus on all the predictors, right?
Mm-hmm.
Remember, like I said, we have limited resource, time, efforts. We can only work on the best to achieve a highest efficiency, right? So that's why you have to be able to compare which predictor is better.
So what's the difference between B and beta? I know one's standardized and one's non-standardized.
No, because remember, you need to use this to write out the regression equation, right?
Okay.
Because you have to use a B, the unstandardized regression width, to write out that formula, y equals, right?
So in function we use B, but then when we're comparing we use beta.
Exactly.
Okay.
Because you still need this one to see, okay, after each unit change, in your predictor, how much unit change can be happening in predictor.
So we just use beta when we're doing comparisons.
Yes, you use beta to do comparisons. That's
Okay.
it. Yeah.
Thank you. Sorry, that was a little
Oh no.
tricky.
I want to make sure you guys understand it before I move on. Okay, Rachel.
Not really.
What's your question then?
I don't understand what it's for. I don't understand what unstandardized is compared to standardized, and I don't know what you use them for.
Yeah, remember before we talk about the regression equation, so you use the unstandardized coefficient, which I said earlier is also called regression weights, to write out the regression equation. Because remember, you have to be able to tell if one unit change in your predictor, how much unit of change is going to happen in outcome. So this is your unstandardized regression weight. Yeah, that's that big B. Of course, when you write it in the regression formula, you have to switch it to the small b. But it's just a mathematical formula.
So if there was a question on the comp about this, what would it sound like?
They probably like, I don't really know.
Like what's the most generalized piece of like knowledge about this? Because I'm not really picking up any of it.
They're probably gonna asking you like whether you should use this or this to explain, you know, the unit change. Oh, I mean, I don't know. Because this one technically you definitely need to talk about this in dissertation. Because you have
Data?
you have to use this to write out a formula in your dissertation. And then you have to use standardized beta to explain which predictor is better in your dissertation.
Okay.
Yeah. But in the comps, I don't, if you do the practice exam, I think there's some questions asking about it.
Okay.
But I forgot which one is. Yeah.
Okay.
Yeah, do the practice exam and.
What page should they go over beta? B and beta?
Oh, it's on page 69 at the bottom. Yeah, to page 70.
69 to 70?
Yeah, it's like the very bottom. Yeah, here 69 to 70.
Okay.
Thanks,
I know, they put it everywhere. It's ridiculous.
Yeah, thank you.
No problem. Yeah, so that's pretty much you need to know about, because you have to like talk about, you know, because after you talk about the total variance, then you have to drag down to each of the predictor, right? You need to discuss them, talk about which one is better, which one is not that better.
Here,
Yeah.
I think I can.
Go ahead.
I think I can help. So, when you're looking at B, it's you're using the raw data to make the predictions.
Right.
But then when it comes time to compare the predictions to each other, they're set on different norms. 5 for one doesn't mean 5 for another.
Right.
So they convert them all into basically standardized scores, which gives us beta, like z-scores, which lets us compare them on, 5 always is equal to 5. So they're all the same, they're standardized. Where before, a 10 might mean very depressed on one measure, and on another measure, 10 might be, moderately depressed. So you want to get them on the same wavelength to be able to compare. That's why we standardize them, and it's called beta.
Okay, so with that, go back to what you said, you use B for what? And then you use beta to compare the predictions.
Yeah, use B to, like Derek said, yeah, that's great, Derek. Good job, Derek. So use B actually to talk about the prediction results or to predicted results. And you use beta to discuss their differences, the differences actually of the predictors. So maybe a better way to say, like, we use a B, the unstandardized, to talk about, like, the outcome, the results. We use a standardized to discuss the predictors. Yeah. So one is for outcome, one is for predictors. That'll be more helpful.
Yeah. Outcome and the results.
Exactly.
And then
So,
the
yeah.
second one was to talk about what?
Predictors. Yeah. To discuss the predictors.
Okay.
So yeah, I can make a quick example. So outcome, for example, it's like income, right? We want to see what kind of factors or predictors going to influence income or predict income, right? So our predictors, for example, predictor 1. Could be, years in college, right?
Okay.
Yeah, and predictor 2 could be your like work performance, right?
Okay.
Yeah, I just assume like we all can measure it based on numbers.
Okay.
Yeah. Okay, so when you do analysis of this, for example, you get out the results, right? So you're gonna have, first of all, you're gonna have unstandardized regression weights for both years in college and work performance. So for example, for this one, the B probably equals to like 2.56, right? And for this one, the B equals to 5.79. Yeah.
Okay.
Yeah, so that's the B. And then next we have their beta, right, which is standardized. So we do that like SPSS. So the beta could be like 0.309, and for this one, the beta equals to 0.620, 624. Better. And we all find out that their P level is less than 0.05, so which means they're all significant predictors on predicting income. So in your dissertation, you're gonna write out, okay, how are you gonna predict income? So for example, I give you a value. I say, I ask you, I say, okay, what if I spend 5 years in college, and my work performance is 80. What's the income I should be expecting? Then how would you know that? You write out this formula. So you're gonna write out the income gonna equal to, oh, I forgot, so let's make up a constant. Let's just say our constant is like 20K, right?
Okay.
This is 20,000. So you're gonna write out this formula, so it's gonna be A plus BX, right? So it's gonna equals to, first of all, write out the constant, so that's 20,000 plus, so you're gonna use the B, right? You have to write out the formula, that's why you need the B, the unstandardized. So it's gonna be 2.56 times years plus, and the work performance B is 5.79, times performance. So that's your formula you need to write out. And now you can say, okay, people ask you, okay, if I spend 5 years in college and my work performance is 80, you punch these numbers into the formula and you calculate it, right? You can have a number of income.
Right.
Yeah, and now you can answer that person, okay, this is the income you can expect because I run the regression and find out the results.
And the 80 and the 5 would be the
that's the person give you a number.
Person's score.
They can give you any numbers, right? So you see, with any given number, you can calculate how much income they should be expecting. That's what we call prediction, right? Because you're predicting. Yeah.
Okay.
So that's part how you use the B.
Okay.
So use the beta actually, and then we're gonna compare the beta. Which one is bigger? Is it 0.6224 bigger or 0.309 bigger?
The 0.62.
This one is bigger, right? So which means that this is a higher contributor, or this one has a bigger predicting power than the years in college. So which means with a more work performance, you can have like a better income compared to more years in college. Which means we know that work performance is more important than years in college, right?
Right.
Because remember, you can spend like for example 20 years in college, but if you don't perform well, your income could still be really low.
So is that what?
So that's what beta
Beta
does.
is for. Okay, so
Yeah.
back there when you were saying that the standardized is to compare and talk about the predictors.
Yeah, because
So
see, you
that's
compare the
when-
predictors.
That's when you would say exactly what you just said. It's
Yes.
like we looked at the beta weights and
Yes.
this contributes more, so work performance contributes more because the number is higher.
Exactly. Yeah.
Okay.
Yeah. So that's how you use the B and beta because you need both.
Okay.
First of all, you have to be able to predict income, and then second of all, you have to say which predictor is better, right?
So the B is to go into the formula,
Yes.
and then
Beta
the betas
is
are
to
to talk about the.
Exactly.
Okay.
Yeah.
Ding.
Yeah, because remember, when you predict this, and what if people ask you, then should I spend more years in college or should I work better, right? Because
Right.
remember, like I said, we're people. We only have limited time, limited efforts, and limited resource.
Right.
We cannot, we spend lots of years in college and also we can work really good. That's, most of the cases, not gonna able to happen. So that's why if people ask you, you're gonna give them the best solution, right? You're gonna tell them, okay, I'd rather to want you to focus more on your work performance rather than, spend more years in college because this one is a better predictor. So you can have more income, right? Yeah. So
Right.
that's why beta is also important in the regression analysis.
Okay, that makes.
Yeah, well, that much better?
Yeah, much better.
Okay, good.
Thank you. Thank
No
you.
problem.
Don't erase the bottom real quick. I'm gonna
Okay, sure, yeah, no problem.
take notes if that's okay.
Yeah, I will just pop this part.
Now I'm going to remember it by this example.
Yeah, you see, that's what I'm saying. Stats is a very strongly ethical subject. You have to really start doing things.
Yeah.
That makes sense, yeah. Otherwise,
you
if
have
you
to-
just talk about it, it's not really gonna, help you to really know how that work.
Yeah, you have to apply it.
Exactly, yeah. Yeah, so when you do research, actually, it would make perfect sense. Yeah.
Yeah, I think that really helps.
Mm-hmm.
It's like the second piece of the puzzle. You can't make a puzzle without the second.
That's right, yeah. So,
That was a really good example.
I know, I think I've used that example for so many times.
Yeah, that's a great example. Thank you.
Yeah, no problem. Yeah. So yeah, you can imagine that if, for example, could be your PTSD or BDI, and you have predictors to see which one is the better predicting. So you can tell your patients, okay, I want to treat you in specific area, right? Because as a therapist, you want that patient to focus on the best part, can treat whatever symptoms or disease that person have. So you can use the least efforts or focus on just a tiny part and to make a huge improvement. Yeah, that's how we go, right? In the practical world. Yeah, that's what stats supposed to help you in this way.
So how would you put it into words If you were trying to talk about, in the write-up of your dissertation, you would say work performance is contributing or predicting more?
Yeah, either way. You can say contribute or predicting. They're pretty much the same thing. Yeah. Those pretty much you can talk in English.
Yeah.
Other than, it's not really strictly the stats wording.
Yeah.
But when you talk about this beta or B, you have to say they're unstandardized or standardized. Those are stats terms.
Okay.
Yeah, but when you discuss the results, which are the implications, right? So that's actually you're supposed to talk in English. Because you have to take the regular people to understand what you're trying to do. Yeah, you cannot say, oh, my unstandardized B indicated this, my standardized beta indicated that. They were like, what the heck is that mean? Yeah.
Like me, 15 minutes ago. Huh?
I know, yeah. Yes, but when you talk about results, it should be, make sense and comprehensive, so regular people can understand. This is what we're doing, and now I understand. Because now they know, okay, I should just work better, make high work performance, other than spend
20 years in college.
Yeah, more years in college.
Yeah,
because that's not gonna do better than working better for work.
Yeah. Same thing like for comps, not for comps for internship doing APA.
Mm-hmm.
Like certain things are better predictors than others.
Exactly. Yeah.
Like ours was like assessment hours, practical hours, like on dissertation.
Yeah.
That's what Dr. D used in class.
What were some of the best predictors?
Assessment hours.
Assessment hours and
how close you are to finishing your dissertation.
Okay, good with regression weights. Okay, awesome.
Good. Yes, thank you.
So no problem. The next component is it's called incremental variance, and that one is on page 70, like at bottom. So actually, this part is very similar to the partial and the semi-partial correlation we talked about earlier under the correlation section. But because it's in regression, so they gave them a new name. It's called incremental variance. I don't really find quite a similarities among the wordings, but the package says that. Yeah.
So they're similar, the same as partial and semi-partial?
Yeah, they use the partial and semi-partial actually theory to explain incremental variance.
Okay.
Yeah. But mathematically, they're the same thing. Yeah. But they're just changing the stats wording. And so we're going to draw the same Venn diagram. I think I forgot to write it out yesterday. I think it's supposed to be like this, right? Venn diagram.
Yeah.
Okay. We're going to do the same thing, but instead of to write out variable 1, 2, 3, now we know this is your outcome, right?
Okay.
This is your predictor 1 and predictor 2. Yeah. So that's another difference. I want you to focus when you draw the Venn diagram for correlation and for regression, you have to draw them a little bit differently. In correlation, you can draw as V1, V2, V3, which means they're just variables. It's not to say one is outcome or the other one is what. But in regression, you have to know which one is the outcome and which ones are the predictors.
Okay.
So the same thing, we have A. I will just follow the chart on page 70, although they have a minor mistake, I think, when they put it into the word. If you look at the letter A, it's outside of the circle. I mean, the part is supposed to be So it's supposed to be like this.
Okay.
So the D is very easy. We already know that's the residuals, or the unexplained variance of the outcome. And actually, when we do regression, when we do partial and semi-partial, so if you look at the word, it's called a variance. So which means we cannot just focus on the correlation. So that's why if you look at the page on 70, so right now when we talk about partial and semi-partial, you need to calculate the variance. So which means they have a more complicated formula. So for the partial, actually for x1, so it's still the partial, but it's gonna call like the part. It's gonna be called the incremental variance of predictor x. So it's gonna be the partial incremental variance of predictor 1 on outcome, and the formula is gonna be a divided by a plus d. Yeah. So that one is the partial incremental variance of predictor 1 to the outcome. Yeah, the formula is also on page 70.
Partial incremental.
Yeah, so the partial incremental variance of the predictor 1 to the outcome.
So is A
Divided
partial?
by, yeah, a plus d.
So that's a formula to get,
Yeah, that's the
A.
formula to get the partial, yeah.
but visually it is the section that A is.
Yeah, visually, of course. But remember visually, because this is just the correlation.
Right,
Because remember we're talking about variance.
right.
So actually they're different, right? Because remember we talk about correlation and variance. Correlation is just how they're related. But the variance means that how much portion you can explain from the predictor to the outcome.
So the semi-partial, so is the partial, does the partial include A and B?
No, just a divided by a plus d.
Okay.
Because mathematically, yeah, but I mean visually, visually it's supposed to be a plus b.
Right,
But
okay,
mathematically, it's a divided by a plus d.
right,
Yeah, it's a. That's the mathematically way to describe it.
but it
But
doesn't include, so visually, the
Yeah,
partial
Visually,
includes
because
A
remember,
and
look
B,
at visually. This is just a partial correlation.
and then the semi-partial is just the A.
Yeah, just a.
So the formula to get A,
Yeah, but formula to get a partial variance is a divided by a plus d.
okay,
So
This
how much?
is just a partial correlation. That's not the variance. Yeah.
So what does A predict that is not predicted by something else?
No, a is actually, remember, a is the semi-partial correlation.
the semi-partial, yeah.
Correlation, yeah, of
A-
predictor 1 to
A
the
plus
outcome.
B would be the partial.
Yeah, a plus b with the partial correlation of predictor 1 to the
Mhm.
outcome d. Yeah, to the
Yeah.
outcome y. Yeah.
Right,
But to get the partial incremental variance of the predictor 1, to the outcome, this is the formula. You use the semi-partial correlation divided by the semi-partial correlation plus the residuals.
because you have to add it to the whole thing.
Yeah,
and
you have
then
to add up the residual and
To
find out how
see-
much variance. Yeah, you can
It'll
count
give
it
you
out.
like a percentage.
Yes, exactly. Yeah, or like a decimal. Yeah. So the same thing for predictor 2, it's going to be C divided by C plus D. So that's to calculate the partial incremental variance of predictor 2 to the outcome.
And both of these include the space where B is, right?
Yeah.
Because we're looking at the partial, we're not looking at the part.
Yeah.
We're not looking at the semi-partial.
No, yeah.
Okay.
Yeah, this is just this is how you calculate it, but we call actually they're different. They're similar
Yeah,
as the partial. Yeah.
Got it.
So to calculate the semi-partial incremental variance for the predictor 1, the formula gonna be so. Well, let me. Can I write them out now?
Yeah,
Okay.
yeah.
I just wanna make sure.
Yeah,
I don't have a space anymore. Okay, to calculate the semi-partial, incremental variance of the predictor 1, to the d, to the outcome.
can I try and take a guess?
Okay, sure.
Okay, would it be A plus B plus C plus D, and then underneath okay, so it would be something divided by all of that.
Yes, exactly. You still have to be, because remember you have to get like
You have to get a percentage.
percentages. Yes.
So it would be A minus B divided by A plus B plus C plus D.
No,
No.
it's actually still A divided
Just
by
A.
yeah, A plus B plus C and plus D.
Okay.
So now you
But
kind of,
doesn't that? Okay.
so remember this is just a mathematical, okay?
Yeah.
I mean statistically or theoretically, you're looking at just the correlation, okay,
Right.
how they count onto. But mathematically, it's a little bit like more complicated. I know it doesn't make like graphical sense, but that's just the math sense, yeah. So you don't really have to. So actually,
Yeah,
the
that makes
things that
sense.
yeah.
So that's for semi-partial.
Yeah, because semi-partial means that you take out even more.
Yeah,
You know,
it's just
contributions out.
what it uniquely provides.
Exactly. So
Without
that's
the
why
overlap.
we need to count off all the the residuals because we see B and C as residuals because they're not supposed to be influencing the unique contribution from predictor one. So that's why we want to take them out. That's why we add them up there here. Because if you notice that this one value is definitely going to be smaller than this, right? Because the
Bigger on the bottom.
yeah, the denominator is exactly the same, but the denominator is
Maybe larger.
yeah, it will be larger. Thank you. So if this one is larger, it's actually make the whole value is going to be smaller.
The percentage that it contributes.
Yeah. So another thing is that you know that semi-partial is always smaller than partial. Not only for the variance, but also for the correlation. Semi-partial is always smaller. Because remember, in semi-partial correlation, it's just A.
Just A.
Partial correlation is A plus
B.
B. So apparently that one is definitely smaller.
Yeah.
So the same thing applies here. Semi-partial is also smaller than partial incremental variance.
Okay.
So this is for predictor one, yeah. So and also the same thing, you know, for predictor two is going to be C divided by A plus B plus C plus D.
Yeah, that makes sense. Cool.
Okay, so that's like a minor difference between regression and correlation. They still use the partial semi-partial theory, yeah, but like they do it a little bit differently because we're looking at variance.
Yeah. Okay.
Yeah, because we're
and
trying
they call it incremental variance?
Yeah, that's what they call it. Yeah.
Okay.
Yeah, thank God you don't have to go through SPSS because on SPSS they call this differently again. They call them zero order. Remember they call them parts.
Yeah, parts.
Yeah.
I remember that. Yeah, I have to circle that on the test. Downbergs. The part.
Yeah, but that's more related with how SPSS call it, so you don't have to really know SPSS like how to do SPSS.
Yeah. I have a question real quick about the comp. Did you get the email about us having to take two comps, the two versions?
No.
You didn't?
I don't check my line email.
Dr. Dallenberg sent out an email the other day, and I don't know if you know anything about this. Like Friday?
Friday after.
What's today?
Like in the afternoon?
Sunday? I think it was Friday afternoon.
Yeah.
She said that if you're taking the upcoming methods comp, you have to take both versions. The first version is like multiple choice, like they've always done, and the second version is SPS. It has two parts. There's an SPSS part, and then it's a write-up part.
So you have to take both?
That's what I emailed her back, and I said, you have to take both, or what? And she
sense.
said, yeah, you have to take both, but if you pass one of them, then you pass your comp.
I think they're seeing if somebody has the knowledge to pass one, they also have the knowledge to pass the other. It's their experiment.
Yeah, I think they're just using this to see what knowledge base we have.
Yeah,
but I'm not going to study for the SPSS version. I'm just
I'm
going to
not
study
either.
for this.
No, that's ridiculous.
I'm not either. So we have to.
And I'm going to take
You have to make
this one first.
Yeah.
You have to make an appointment.
You have to make an appointment with Rich before the 30th of January.
For what? Take the second
To
one?
take the second version.
Oh.
I don't know if you have to email him before the 30th or make the actual appointment before the 30th.
Yuck.
But I emailed him.
Oh my God. Yeah, I don't know.
So we
any
have
of
to
this.
take.
Yeah, Richard just told me follow the old pattern, traditional pattern.
Oh.
Yeah.
Okay.
I thought they're not gonna even do this until like June.
Yeah, I
They're
was
just trying
hoping
to make
that
our lives fucking difficult.
I thought that they were gonna give us a choice.
Yeah, they are giving us a choice. They're just doing it this way to get data.
Yeah, to try and see who. Well, they'll see very quickly that no one knows SPSS.
I know they don't really do a good job on explaining SPSS to guys technically.
No, I don't feel like I know SPSS at all.
Yeah, because most of the guys up here, like, I know you know stats. Actually, some of you really know stats, but when it comes to SPSS, you feel like, oh, what? Yeah.
Yeah.
Yeah. Okay, so that's that. And we have like the last part of regression that we need to go through. I mean, technically for me, it's not that important, but
It's on the packet.
yeah. I mean, I never really focused that much on that section. However, Packet like really heavily, or Dr. Gewirtz is really heavily, like a huge player on that. So I will keep my like opinion comments quite away. So it's on page 72. And actually, it's part of, they put it under part of the assumptions, first of all. if you look at that page 71 at the bottom, they talk about independence of errors. Remember, we discussed that. That is one of the assumptions. You will have to make sure that the residuals, they're uncorrelated, they're independent from each other.
Mm-hmm.
But then if you flip to page 72, they talk about that's not only the error you should be looking for. They said you also need to be looking for the specification errors.
What page is this?
Oh, that'll be on page 72. Yeah, so the next component is just like, I would say it's others, because I don't really.
Where it is.
Yeah. So the first one is like have something to do with independence of error, which is actually assumption. Yeah, I mean page 71 makes perfect sense when they explain this. But when I go to page 72, they start talking about this specification error. So they said the relationship between the variables must be linear, but that's the assumption of linearity, right? We just talked about that. And then they say all relevant predictors must be included. I was like, yeah, come on. And then they say no irrelevant predictors can be included. I was like, seriously? So I have no idea what they're trying to say, because I don't know if it had anything to do with specification error. So it just seems like you have to make sure the linearity was satisfied to not to have specification error, and at the same time you have to make sure all the relevant predictors are included in your regression model. I was like, yeah, I was like, that's my study. I was like, of course I'm going to include it. And then the last thing is like make sure no irrelevant predictors. I was like, if I'm not going to study any irrelevant predictors, why would I include them?
Put in the good stuff, remove the bad stuff.
Why would they even say that?
So I have no idea what this whole specification error is about, but because it's on the on packet, so I'll just put it there.
Oh, well.
Yeah.
Well, you should rewrite the packet.
Right, I know. Richard and I would be talking about that. But if they're going to change the format, then probably it's going to be a little bit different.
Yeah.
Yeah. We'll see. I'm still working on my new version, actually. And the next one, they talk about this measurement error. So it's in the same page. It's just following the specification error. They said the measure should be reliable and valid. That one actually makes sense, but I mean, of course, every time when you measure your variable, right? When you measure your age or income, you know you're using the money to measure income. You're not using, like pound, or whatever the weight or length to measure income. I mean, of course, apparently. So I don't really know why they put these two up there. So I just put up there because the packet has it. And the next one is actually they're talking about the shrinkage. Which is like a favorite term that discussed by Dr. Gewurtz, I think, in his class. Yeah. Or Dr. Glazer, I forgot which one.
Who did you take stats with? Dr. Glazer?
No, I'm in business.
They have their own teachers?
Yeah, we have I only took one stats class. And actually I took it when I was a master. I didn't never take any stats when I was doctoral students. So back then it was this visiting professor from South Korea, actually, who tried to kick me out because he found out that I was a master student back then. Because all the class students it's a stats for the doctoral students.
Yeah.
But because my program director assigned me to the wrong class, because of the class coding thing, it's so messed up in business program anyway. So I was there the first class, he tried to kick me out. So
It's hard being the smart person.
stay, yeah, because I know, and we didn't learn anything of this. We just because he was teaching, because that's for the advanced a stats 3. So he taught a structural equation modeling. He only taught how to do that in the whole class. He didn't even talk about any of these.
So you only took one stats class?
Yeah, just with him, and it's back in 2000.
Ever?
Yeah, ever. Like I said, I learned stats in here. I never really learned stats in China. I just feel no, I pretty much start picking up stuff by myself when I start working for Richard. Yeah.
How do you think stats and
Wow.
数理统计。数理统计。统。Yeah, it's not pong, it's tong.
I'm new. Okay, take it easy on me.
T-O-N-E, right?
Yes, T-O-N-G. Yeah, it's like a T. It's like tong. 统计. Yeah. I know you're new. I don't know whether we should record that here, but it's like wasting the time on the recorder. Okay, let's finish the shrinkage. And actually, there's one last thing I wanted to, it's actually the packet has it, and we can talk about it, and then we can, take a break, quick break.
Yeah, that's right.
Because that's the like things. So first of all, the shrinkage. Actually, shrinkage is it's related with actually the model fit or the regression. Let's put it like a regression model fit. It has something to do with regression model fit. So shrinkage means it's to shrink, right? So you can definitely understand the wording like literally. So that means when you collect your data, right, you analyze the sample and build up your regression model, and which means pretty much the theory behind it is that if you're using the same model and apply it to a different data or a different sample, you could have a shrinkage, which means your R square is going to be different from the original model that you have. With the new model, with the new model with pretty much it means with a new sample. So which means you use the same model and you just try to gather like a different sample data. So you're gonna still measuring the same predictor, the same outcome, but you're gonna for example, you already have like 250 people, and of course your classmates or other researchers, they have the same 250 people, but they're from a different population or sample. And they have the same information on the predictors and outcome. So you're trying to say, oh, if my model can be replicated on that sample, right? Because you guys have the same thing, it's just you have a different samples. However, you do this, analysis, and then his results could be going to be very different than yours. So that's going to cause the shrinkage. That's what we call the shrinkage. Yeah. And then you know that there is going to be a gap between these two R squares. Yeah, the original one and the new one.
The new one's not going to be as strong.
Well, actually, there's some there's something about shrinkage. So pretty much we're just trying to say the smaller the gap between these two R squares, the better the regression model will fit, okay. Right? Because that means your model can be replicated like multiple times on different data or samples, right?
Right.
Yeah. So which means if it's a gap, or we call it like an R square change, right? Because from the original and to the new, there's going to be R square change. Mm-hmm. If the R square change is smaller, which means the shrinkage is going to be really small, right? Because you don't have that much of a shrinkage. So if this one, of course, if it's close to 0, or R square change close to 0, that means we have pretty much the best regression model fit. Yeah. That just means your regression model is really good. So that's why sometimes to avoid a large shrinkage, we're not really reusing R square. We're trying to use an adjusted R square.
And how do you get adjusted R squared?
We just talked about that earlier. Remember, we take out the redundant part.
It's the overlap, the B in the middle, since it's counted twice from
predictors,
X1 and X2. Then they'll just remove one of those overlaps and only count the.
Yeah, so it's only count the true variance of the outcome from the predictors. Yeah, so that's why if you use an adjusted R square, you can largely reduce the regression model residuals, right? Yeah, so the residuals of your model are going to be smaller. So that's why if you use an adjusted R square and you do the same analysis with a different data set, with the same model, your adjusted R square should be very similar. So that's why they say that if you're going to assume they could have a shrinkage problem causing, they said that then don't report R square, because the R square change could be very large and it could be actually bias you and give you some inaccurate implications. So that's why report an adjusted R square. So this could be another occasion that an adjusted R square should be applied rather than R square. Yeah.
So it's basically another way to cheat.
Exactly.
No, seriously.
No,
right?
Yeah, that's right.
That's like the idea.
Exactly. Yeah. That's all about lying, cheating, affair, mistress. Maybe that's why I so like him that much. So crazy. Okay, so shrinkage, is on page 72. Yeah, you can just look it through. And so the last thing I'm gonna talk about is, so that's also under others. So there talk is a bunch of, it's technically still under the assumptions of actually of outliers. So you know, if we talk about outliers, it's related with normality, right? Because normality issue is caused by outliers. So that will be on this section is on page 74. Because remember, we already talked about Mahalanobis, right?
Yeah.
Mahalanobis. Yeah. So instead of that, beyond this, they also talk about the other, investigation that a regression should do, which is actually, I think Dr. Gewirtz liked to do it. I mean, I don't really recommend to do the rest because Mahalanobis is like already enough to do, like, checking the normality. But they also talk about the leverage, the DF beta, and the Cooks. So if you go for page 74, they have the definition of these four. So Mahalanobis, they talk about, they gave you a number for each subject, and then the number will tell you how far away that each subject are from the theoretical center of the data. So that's why Mahalanobis can tell you whether you have outliers, right? Because remember, if they're too far away from the center of the data, that means they're too far away from the mean. That means you have outliers, right? So you just delete the ones that really extremely out of there. Yeah. And the leverage is they have each subjects have a number, and those numbers can indicate you like how far each of the subjects are from other subjects. But I mean, I feel like, of course there's gonna be, differences, between the scores. That's why for me, leverage doesn't really do anything. I mean, no matter what, each of the subjects is going to be away from each other, right?
Right.
Yeah. And the next one, the DF beta, they said like each subject have a number on like every predictor that you're trying to include in a regression model. And that number can tell you how much that subject influenced each of the predictors in regression weight. So for me, I feel like it's really talking about like a regression, residuals. Because from each predictor to the regression line, they have these differences, right? Because this could influence in the slope, right, of the best fit line. Because remember, regression width is coming from the slope, right? So that's why I feel like then you just, whatever the best fit line you have, this just about the residuals. I mean, anyway, they just talk about that is important. And the last one is the Cooks. They said Cooks is also, every subject has a number. And using that number, you can tell how much each of the subjects can influence the regression equation, like as a whole. So it seems like you're just talking about whether the regression equation as a whole thing can be influenced. So, yeah. But again, like all these four, technically, is based on the COM packet. They said you should like check each of them to see whether you have outliers will influence the normality. Yeah, so you need to clean them up. But again, for me, like Mahalanobis D is like, strictly enough to check for normality. So,
yeah, that makes sense.
Yeah, but Packet, like this.
Just so we're familiar with the other ones.
Yeah, they're just like talk a little bit more in detail and just blah, blah, blah.
What page are these on?
Oh, 74? Yeah, like in the middle. And there's just one last section is on the top of page 74. They talk about the standard error of estimate, which we already go through. So pretty much that one is just the standardized residual. Yeah, remember when we draw that homoscedasticity chart? Yeah, that's the standardized residual between the observed value and actual value. Oh, sorry, between observed and predicted value. So they just give it's like a better definition. And then the next one they talk about is a statistic control in the multiple regression. Actually, they're kind of like confusing you with covariates, which doesn't make any sense. I mean, we don't really do statistic control in the regression because we only do like mediator and moderator in regression. We don't talk about covariate in regression. So I have no idea how that one is related with ANCOVA.
Yeah.
Because they say that C control for partial out ANCOVA. Yeah, that's part of actually kind of like ANOVA section. So, I mean, practically, I would say just cross this paragraph out because in regression, we don't have these control terms.
Cross that K.
Yeah, just cross it out.
Okay.
Yeah, I believe it's the students is probably kind of confused from the class.
Yeah.
So that's why the students put up there because he probably doesn't even know why ANCOVA is somehow related, yeah. So yeah, so just don't read it because it's also going to confuse you. They have nothing to do with controls in regression. So remember in regression, we just look at how the one score change influence the other score change, right? There's no control part of it. Yeah, it's not like you're doing treatment versus control group. Okay, so that's pretty much all for regression. And any questions before we take a break? No?
No.
Okay, good. I'm ready.
And action.
Yay! Okay, so that's multiple regression. Everything you need to know. Kind of like also lots of things to know. So the next part after multiple regression is we're going to talk about logistic regression and the discriminant function analysis.
Is that the same thing?
Yeah, they're similar, but because the packet didn't, they kind of combine them together. So that's why I'm going to also put them together.
Okay.
Yeah.
Logistic.
Technically, actually, literally, logistic regression is more used than discriminant function analysis. So this section is from page 77. So both of them, okay, from page 77 to 79.
Okay.
The first thing is that logistic regression, as you know that these are still regressions, so you're still trying to predict outcome. So the structure is similar. We have the predictor to predict an outcome. And the difference is actually coming from here. So for the predictors, actually, it could be continuous, or racial. The predictors in logistic regression and discriminant function analysis can also be nominal.
And that's a difference?
Yeah. Because remember, in multiple regression, the predictor has to be continuous. And for the outcome, for logistic regression, is actually the outcome has to be nominal or categorical.
Outcome has to be nominal?
Yeah, nominal or categorical, which means,
and then,
yeah, so which means in the logistic and discriminant, regression analysis, your outcome can only be counted as like the types, levels, groups. You cannot have like the scores. Yeah. So
that's different from multiple regression.
Yes, because remember in multiple regression, both predictors and outcome, they have to be continuous. But in logistic, first of all, predictors can be either continuous, racial or nominal. But the outcome in logistic and discriminant function, in these two regression analysis, the outcome has to be nominal or categorical. Okay. Yeah, that's the first thing. Yeah, but again, it's still predicting, which means between these two, you're trying to build a causal relationship or causality. So technically, it's still regression because you're trying to predict, what the outcome could be.
Okay.
Yeah, that part didn't change. That's the same shared as in multiple regression.
So you're trying to find causality.
Yes, so it's still causality, but it's still regression. And the next, we're going to talk about assumptions again. I really feel like we're going to become a fan of assumptions. Every time we talk about assumptions. Yeah. So here, if you look at the outcome, it's a categories, right? It's a nominal. So technically, there's really no much of assumption needed. Because remember, this is not a score. So which means there's no variance, right? There's no variance changing. Because remember, predictors doesn't matter. Even though predictor is continuous, but that's not the thing we're focusing on. The outcome is the results that we want to focus. So that's why every time we check assumptions, it's more focusing on the outcome. So in t-test ANOVA, we're focusing on DV. So in the regression, we focus on outcome. And because this outcome is a nominal and categorical, so that's why assumptions in logistic regression or discriminant function are very, not that as heavily required as in multiple regression. And if you go for page 79, they're talking about assumptions, and the first bullet they said it's almost impossible to violate assumptions because technically there's really no assumption needed because you don't have a variance in your outcome, right? There's no score change. You're just trying to see which type or which level are possibly going to be happening, predicted by these predictors. Yeah, you just compare their chances of which chance is going to be happening higher than the other one. Yeah, right? Because you're just remember
right. So like,
for example, let's just say your outcome is gender. It's just to see if any predictors can predict will be more happily like happen on male versus female, right? Yeah. There's technically no score change, right? You're just male, female. Which group gonna have like a higher chance happening if that predictor is trying to predict them?
Right. Okay.
Yeah. So that's why it's make logistic regression. The assumption is that very lenient, right? Lenient. Lenient.
Yeah. That's perfect.
Yeah. Yeah, but still there's some basic assumptions we still need. I'm gonna list them up here. Like independence of observation, right? We still have to make sure that, our participants, they're independent from each other. And if you look at the third one, they say the outcome must be dichotomous. So actually that one is, it's not to say it's wrong, because if you're doing a binary logistic regression, the outcome has to be dichotomous. So for example, your DV the outcome can only be like gender, you have a 2, right? Dichotomous means you only have 2 levels or 2 categories, right?
Oh, okay.
Yeah, that's what dichotomous means.
So like,
or like your outcome is like, with the answer of yes or no, pass or fail, go or not go, vote or not vote. So that kind of outcome is called dichotomous outcome. But they put it here is actually they kind of like, make it like not really quite right because we're talking about logistic regression and discriminant function as an overall. But if you're doing a binary logistic regression, yeah, your outcome must be dichotomous because binary logistic regression only do dichotomous outcome. So we only focus on 2 categories.
Oh.
So that's why this assumption is kind of like, so that's why I changed that assumption to the outcome just must be, categorical or nominal. Instead of just saying it must be dichotomous. Yeah, so I should make it. So I just say outcome must be dichotomous or nominal. So it means that it has to be a nominal, but you can have only 2 levels or 2 categories, or like we just say 2 groups. Or you can have nominal means you have more than 2 groups.
So words for the comp can say it's dichotomous, nominal, or categorical.
Yeah, so I think that the assumption that put up on the packet is not quite right. Yeah, because that is definitely wrong. It's not has to be dichotomous because you could have more than 2 groups, right? Yeah. You can still do a logistic regression.
Yeah, you can do a bunch of groups.
Yeah, so that's why I just changed to that. And next assumption is about sample size. They said they need a large sample size, which means you need 20 to 50 subjects per predictor. So I just put sample size here. When you go for a packet, they put a number, specific number. They said if you have like 2 predictors, each predictor at least you need like 20 to 50 subjects. So which means if you have 2 predictors, you need at least 40 to 100 subjects to be able to do the logistic regression or discriminant function analysis. And the last one is actually on the packet. They said that if you do a discriminant analysis, they said you can use it as an alternative to logistic. However, there's more assumptions than logistic. And they didn't talk about it at all.
Are we talking about logistic regression right now?
well, the packet is kind of like, the packet put those two terms together.
Okay.
But if you read the packet, they're more focusing on, it's actually they're focused, oh, hold on, that's the wrong page. Yeah, they didn't separate them up because they're kind of like using the same, the same like indicators or parameters. So that's why they didn't separate them up, but they just say that if you do the discriminative function, you need more assumptions, and they didn't talk those additional assumptions.
Okay.
So I feel like probably these are three assumptions required for both logistics and discriminant. So they said discriminant needed more assumptions, but the packet didn't talk about it, so I don't think you need to spend any more time to find out what are they or, yeah. And I think the COM should be more focused on logistic regression, yeah, other than discriminant. Because even in the classes, I don't think Dr. Govertz, talk that much about discriminant. Yeah.
No, a lot of talk about logistic regression.
Yeah, so that's what I'm saying. But in the COM, they kind of put the two terms together. You just need to know when you do discriminant, outcome still has to be categorical phenomenon.
Yeah, that makes sense.
Yeah, but I think we can just focus on logistics.
Logistics,
Yeah.
yeah.
Oh, actually, I'm sorry. It's right here. If you go page 78.
Could contrast discriminant analysis.
Yeah, they have the discriminant analysis on some assumptions.
Yeah.
They put like normality, linearity, heteroscedasticity, and they spell heteroscedasticity wrong. It's supposed to be SCE, not SKE. And independence of observation is right there. Yeah, but again, you don't really have to know that much about, the assumptions for, logistics, because logistic regression is not that heavily required in the COM.
Yeah.
So we're just going to explore like the important terms or the components in there, and then we just move on. So for the assumptions, these three you definitely have to satisfy. And I think they should be on COMs. But for the further ones for discriminant, you don't really have to do, think about that. Actually, if you look at, because the outcome is a category, so remember when you draw the scattered plots, your DV just have two values, right? Because let's just say this is your outcome. You're not going to have a score. So let's just say if you have a different scores people, so it's going to be just either like, or it could be like, so let's just say if we set one as, one category, and we only have two categories here, so probably one is a male, so that's the outcome. Two is a female. So you only have like, these are gonna be, your predictor. So it's only possibly that your data, the scatter plot is like this. Right? Because for each person, they're either in the male or either in female, right? Yeah. Right. You see, it's not like a scatter plot. It's just like a bunch of a dot into like different categories. Yeah.
But not in both at the same time.
Yeah, exactly. Yeah. So when you have a predictor value, they either for female or they either for male. Yeah. So that's it. Yeah. You see, that's why you don't have a scatter plot or linear relationship. Yeah. Because your outcome is actually a categorical variable. So that's why it's going to be a little bit different when you talk about the results, from logistic regression, because technically you're just looking at whether female has more results, has more people dotted on it, or whether male, has more predictors predicting on it, right? That's what you're trying to do is actually. So that's why in logistic regression, there's a bunch of key terms, which is going to be very different than the multiple regression because these categorical outcomes. So the first one we're going to talk about is -2 log likelihood. And usually we combine this one, we test its significance using chi-square. So this one is to assess model fits or the logistic regression model fits. See if your logistic regression model is a good model to predicting which outcome has a higher percentages of happening in which categories. And so which means we want the chi-square to be less than 0.05 to indicate that it is a good model, right? If p is bigger than 0.05, that means your model is not good, it's very bad. That means you need either need to adjust your predictors or kind of changing your model, because apparently your predictors is not predicting the categorical outcome. And the next one is called Cox and Snell, or it's
Nagelkirky.
Thank you. Nagelkirky, because technically I never really run any regression or help any people, with doing a logistic regression in their dissertation or assignment. So that's why for me these terms are kind of like bizarre. And it's a pseudo. Pseudo R squared. Actually, this is like, so you can, it's a Cox and Snell, that's the person's name. They actually invented a formula to calculate pseudo R squared. And this is a Nagelkirky, that's another guy, to calculate actually R squared. So this one is actually similar to the effect size and R squared in multiple regression. But remember, if you look at outcome, because remember R squared is talking about the total variance, right? Because remember we have that little circle. It's the total variance can be counted for by the predictors, right? That's R squared means. Right? And remember, it's variance coming from the score change. So, but if you look at outcome for the logistic regression, there is no variance. We just have two categories, right? So actually, technically, there is no score change. So which means we don't even have a variance. So technically, there's actually no R square. So that's why these R square is actually, that's why we call it a pseudo R square, because it's not like an R square, because like you don't have variance, right, in your outcome. So that's why in logistic regression, R square is not as important as anymore. Not like in multiple regression. Remember, R square is very important because we have to talk about how much variance can be explained if the model is like a good model, if it's a large effect or a small effect. But in logistic regression, R square is not as important, and because there's a different people, they calculate R square using different formula based on what they thought was supposed to be calculated. So that's why R square has a very, like a bad credits. To believe that this is the real effect size for our regression model, logistic regression model.
Can I ask you a question?
Sure.
The -2 log likelihood.
Uh-huh.
I don't understand what that means.
Oh, that one just to assess the model fit. So that's why they use a chi-square to look at if the logistic regression model is a good model.
Why does it say? Why don't we just say chi-square? Why do we have to say -2 log likelihood?
Yeah, this is a statistic. They use a chi-square to prove if it's a significant statistic.
Mm.
Okay, so you just use a chi-square to see if it fits the models. Significant.
Yeah, because for -2 log likelihood, it's just like a mathematical formula.
Okay.
So they use that formula to calculate number, but then they don't know if that number is significant or not, right?
Perfect.
And then they use a chi-square to determine if that number is significant or not. Yeah.
Mm.
So that's why, they put it there. But it's supposed to be a -2 log likelihood. Yeah, another thing that remember in stats is actually stats. All these statistics, they calculate them based on mathematics.
Yeah.
But of course, you don't have to know how to do it. What's the formula behind? So after the the Cox and the Snell, next one is the Hosmer and Lem show goodness of fit chi-square.
I remember that.
Mm-hmm.
Yeah, so you can see actually logistic regression is more like about like just. Like you just want to know whether male, for example, let's just say if our predictor, like to say this one is age. For example, we just want to say if younger person are more like a female or younger person are they're more like if younger person are male or younger person are female.
More likely to be
right?
female.
Yeah, exactly. Yeah. So that's why we just do just regression. So that's what they're doing.
Okay.
So like that's why you see logistic regression has all these weird things compared to multiple regression because your outcome is categorical. Why you're kind of predicting just the chances or the odds.
And what page are we on right now?
Oh, 77? Yeah.
Cool. So I keep going back and forth.
Yeah, so you're kind of just predicting, what's possibly which category could be likely to happen following
Right.
that predictor. Yeah.
Okay.
Yeah, so it's more like odds, chance, probabilities.
Mhm.
Posner and Lenshaw, so next one is goodness of fit. Chi-square. So actually, this one is really similar to the function. It's function like the negative 2 log likelihood. It's just telling you whether the logistic regression model is a good or bad model fit. But if you look at the package, they kind of separate as a differently. So they said negative 2 log likelihood is to say whether the whole model are predicting the outcome. But then this one, the Hosmer, they say if the predictions we're making fits the actual data we collected. But pretty much it's actually the same thing. But the thing is that for this one is actually you want the p-level is bigger than 0.5.
So that's the difference.
Yeah, that's the difference between this and this chi-square. Yeah. So for negative 2 log likelihood, it has to be less than 0.05 because they all use a chi-square.
Yeah.
This one uses a chi-square, this one also uses a chi-square. But this one is you want it to be bigger than 0.05. It's actually, this one is more like they're using the chi-square as a goodness of fit. Because when we do the goodness of fit test using chi-square instead of a test of independence, we want that chi-square, the p of the chi-square to be bigger than 0.05. So these chi-square, you can see it is actually, we're doing it as a test of independence.
Okay, and that's why they're opposite.
Yeah, exactly. Yeah, when we use a chi-square as a test of independence, we want the p-level less than 0.05.
And that's not significant?
Oh, p less than 0.05 means significant.
The bottom,
Yeah, this one doesn't mean significant.
Okay.
Yeah, this one means that if it's not significant, that means your model is the same as the perfect model.
Yeah.
Yeah, so that means your model is exactly the same as a perfect model, so there is no difference. That's why we want to know significant. This one just means that our model can predict the results in the best way. So it's kind of like.
So do we want it independent or we don't want it independent?
It's kind of like we do want independent because we want to be able to tell there is a difference between male and female.
Okay.
Yeah, but this one is kind of like more focusing on if there's a better model out there, whether your model could be different or the same as that better model out there. Yeah.
Okay.
And the last one, not last one, not that, this the last one. We're talking about this predicted probability. Let's see if they talk about it. Predicted probability. So actually, this one, we also call it expected B. I don't know if you're already familiar with that term.
No.
Yeah. So this one is like, it serves as like a regression rates, in the multiple regression. And it's the unstandardized regression rate. Oh, hold on, it's the standardized regression rate, sorry.
So predicted probability is the standardized.
Oh, hold on, it's the unstandardized.
Unstandardized regression rate.
Yeah.
Let's call it XB.
Oh, hold on, predicted probability.
B?
Yeah, it's actually EXP, parenthesis B, parenthesis finish. Yeah, so I should take this off. Because in SPSS, it shows like this. Yeah. So if you have a value, so for example, let's just say age versus female male. For example, if your X is B for this one equals to, let's just say 2, and let's just say we set male as a reference category, that's how you do actually logistic regression, but it's more like an SPSS procedure. I just want to quickly explain how you can understand this term. So for example, if we calculate this one as a 2, and the male is a reference category, which means younger female, let's just say age, because apparently these are older. Let's make it more older female. That just means with age increased, there's a chance that female has a 2 times chance higher than male to be older. Yeah, that's just how you interpret it. Like that's what predictive probability is. Yeah, so which means with age increase, right? Because that's how, because remember every time we talk about regression, we say when IV increased, whether DV increased or whether outcome increased or decreased, right? That's in the regular multiple regression.
Can we switch the example to, say, an outcome of, like, lung cancer?
Oh, sure, no problem.
That might help me understand it a little bit better, because when you're predicting whether someone will or will not have
Okay, so
cancer.
Okay, so whether we have cancer or no cancer, right?
Depression. Cancer's kind of depressing.
Okay, so what do you want? One
Depression.
One has cancer or 2 means no cancer? Or?
Let's do depression.
Okay, so one
yes depression and no depression.
Okay. So 1 means like probably 1 is no, right?
Yeah.
And 2 is yes, and that is depression.
And we can have as many predictors as we want with logistic regression, right?
Yeah, the same thing, but I just make it 1 to make it easier to understand it. Yeah.
Okay. So depression.
So the predictor, you want to what?
How about a depressed parent? Because in the bloodline, depression.
No problem.
Right?
Well, that'd be dichotomous.
Is that not a good predictor?
No, you can have that's what I'm saying. You can have nominal or continuous predictor. But I just have to kind of change.
So what would a nominal predictor
So let's
be?
use a nominal. So let's use age.
Do you want to speak with age?
Yeah.
No, you can use a nominal predictor. It's really up to you which way you can understand it better.
We can use a continuous or a nominal?
Yeah, because remember in the logistic regression you can use either.
Okay.
Because remember outcome is categorical, so it doesn't matter.
It doesn't matter what the, okay.
Yeah.
All right. Yeah, we can say age.
Yeah, okay. Okay.
I think this will help me understand it a little better.
So let's just say, okay, I'm just going to redraw that to make it, okay, so currently, let's just make it sensible. So which means younger age, they're less depressed, okay? That means they're no, and with getting older, you're more depressed. You're possibly, you're going to always depressed, right? Yeah.
Okay.
And let's just put the age range is between 2 years old to maybe 50. Is that a good range?
Sure.
Yeah. Okay. Let's just collect a bunch of people. They're ranging from 2 to 50.
Okay.
All right. So that's pretty much how you draw the plot, because I understand that plot probably make it much better. So if you just simply look at a plot, you can tell that okay, there's definitely more possible chance that the elder people have like a depression than the younger people, right?
Mm-hmm.
Yeah, so that's what you're gonna come up with results. But you have to look at expected B to tell how much chance, like how much more likely that, elder people will have like depressed over like the younger people. So that's why we need to calculate this, and that's what logistic regression does. So for example, if we have the expected B and it's equals to 10, that means for every unit change on age, so for example, if you change from age 2 to age 3, you will have 10 times to have like a depression over the no depression with your age increased. Yeah, so that means if you increase from age 2 to age 3, of course I make the numbers a little bit higher, but I'm just saying it could be any number based on the calculation. But I'm just saying if you increase from age 2 to age 3, you will be 10 times higher on your depression level. So which means you're probably gonna be, from like you're gonna be like 10 times higher to have a depression compared to not have a depression. Because right now you're talking about probability, right? Because you don't have a score on depression. It's just yes or no. Yeah.
Okay.
Yeah.
So that's comparing how much more likely.
Yes, exactly. Between the categories, yeah.
Okay.
Coming along with how the predictors changing or increased.
Okay.
Yeah. I know it's a little bit like a bizarre, but yeah, because it's not really, because we don't have a score, so that's why not really able to tell how the score changed on the outcome. It's just more like which category is possibly happening. Or in the other way, you can say if age changed from 2 to 3, to have a yes depression is 10 times likely to happen than a no depression. Yeah, that could be another way to say it. Yeah.
Okay.
Does it have to be linear? Can it change? Like, could it go to
No,
like?
because it's not linear. 'Cause remember, your outcome is categorical. There's
Okay.
even
So
no
it
linear.
could go no, yes, and back down to no. So like, after you get pH 50, you shouldn't be depressed. Can you do that?
Oh yeah, I mean it's possible. I mean, of course, there is a possibility that you could have like a few of them, and then you can, for example,
Yeah,
like this. Yeah, it's
okay.
definitely possible. Yeah, but I'm saying that I'm just fake up the results.
Yeah.
But you're gonna look at expected B
Okay.
to see like if you have expected B, and the important thing is that because we set up a reference group, so this one could be actually 0.35. Right?
Yep.
If it's a 0.35, that means the chance to have no depression is actually higher with the age increase.
And for the comp, because I remember this now from class,
Yeah.
do you think we'll have to calculate this?
I don't think so. It's a very complicated formula. Because if you look at packet on page 77,
Yeah.
that one is like 1/1 plus like an E.
Yeah, we used to have
And
to
yeah.
do these with EXP.
Yeah,
with
that's the formula. That's
expected
to
B.
calculate like A plus B1 x1.
Yeah, no, it was a pain in the butt in class.
Yeah.
Okay.
So yeah, I don't think he can ask you guys to calculate that, but it doesn't make any sense.
Yeah, I hope not.
Yeah.
Thank you, Longshu.
Yes, thank you.
Okay. Just stop saying that. No, I feel like I got paid for doing this, okay? So don't feel,
Tomorrow we're gonna bring you
Stop bringing me stuff. You guys are broke.
we're gonna bring you a
okay?
doggy tomorrow.
You really want to bring me a car or house?
We're gonna bring her a chow.
I was thinking that this morning. I was like, God, I wish I could just bring Brooklyn and have her hang out on the floor.
You could.
Could I?
You're not supposed to, but who's gonna come on?
Wow.
I wouldn't.
Nobody.
But I wouldn't pay attention, I'd just play with the dog.
Yeah. She's so good. She just sits quietly. She's getting old.
Okay. So after predicted probability, the next one is classification table. That's kind of another term you need to know about, just regression. So this one is actually telling you, so actually this one is kind of like serving as the effect size, Not really effect size, but it's kind of like, serve as the rule as effect size. It's telling you how much better you're predicting your results, or how much accurately you're predicting your results.
Okay,
Yeah.
okay.
So classification table going to give you a percentages. So for example, let's just say if it's a 70%, of course you don't have to know SPS has calculated. They have like a formula. So this number means that to calculate this expected B of like 10 times higher between the category outcome, you are 70% accurate. Yeah. So that's why I'm just saying it's like the effect size. It tells you how great these results could be true or not true. So this one could be like a large effect, right? Because most of the time you're 70% right about these, results. That, we have like more depressed, like 10 times higher than no depressed. Yeah. So that's what classification table. So this actually is like the real R square, but of course it's not R square. But it's like R square in multiple regression is giving you like a relatively effect size.
Classification table?
Yeah, it's called a classification table. And if you go for page 77, they also call it hits and misses. It's like a cute name, hits and misses. Yeah, so it's pretty much what's the percentages you can hit the right answer, and what's the percentage you're gonna miss the right answer. Yeah. So that's why you see you're 70% gonna hit it, which means you only have like 30% gonna hit it wrong. Yeah.
Okay.
I remember these.
You do?
Uh-huh.
Yeah, so that's why that's how they actually, from classification table, they actually put out like the two concepts. One is called sensitivity, and the other one is specificity. That one reminds me of nightmare.
Nightmares, yeah.
Actually, I'm gonna give an example. So just use our depression. Because first of all, sensitivity is talking about you can predict depression, or the chance of having, predict the chance being depressed. Being depressed versus, non-depressed. And actually, I should say accurately predicts. So sensitivity means that, so I'm just going to use our example to explain the term. So sensitivity means that you accurately predict the chance being depressed versus non-depressed, right? That makes sense? So that's why the 70% here is actually our sensitivity, right? And actually specificity is also accurately predict the chance in anything else but trust. This is non-depressed. Okay, specificity means that you accurately predict the chance being actually anything else but depressed versus non-depressed. So you see, you're not really predicting depressed, you're predicting something else.
But
that's what specificity means.
Specificity.
Specificity.
Isn't it the ability to predict anything but depressed, not depressed, and non-depressed?
Yes, actually, you're not really predicting, anything with anything about depressed. You're actually predicting something else. For example, you could be probably predicting, for example, like having fun, or predicting, being happy, or predicting being, like joy, or
like a.
Yeah, but you're not predicting like depressed versus non-depressed. You're predicting something else.
Something else outside of your.
Exactly. Yeah. So that was specificity. I mean, in the concepts, that what means. So actually here, specificity is actually, specificity and the sensitivity, they kind of have these relationships. So actually,
they're opposites, aren't they?
No, actually sensitivity.
Isn't it like a true positive and a.
Yeah, so actually this one is
true
like
negative?
it's called false positive.
False positive?
Hold on. Let me see.
No, true positive.
Oh yeah,
and
true
negative.
positive, true negative, yeah.
True positive and true negative?
Yeah, this one is a true negative, sensitivity is a true positive.
Yeah,
So
because it's
specificity is the ability to
yeah,
detect
because you're predicting the wrong thing.
the absence of the outcome.
Yeah, exactly. That's why it's a true negative.
It's a true negative because
Yeah.
they're not really what you're looking for.
Exactly.
It's like a false positive.
That's right.
Yeah.
But false positive is type 2 error. It's actually you're making mistake on measuring the specificity. Yeah. So that's what's false negative. Yeah. So that's why if you cannot accurately predict the chance being anything else but your outcomes, you're making a type 2 error. That's related with specificity. And if you're not accurately predicting the chance of your outcome, you're making type 1 error on sensitivity.
Yeah, there was a box either in this packet or in one of the PowerPoints online.
Okay.
So,
It was a
You mean like
it
an
was a-
RLC curve?
it was like a 2x2 box, and then it explained how sensitivity
Yeah,
was related to
yeah.
type 1 and how.
Yeah, they're related to type 2. It's actually, the other
It's
thing,
a-
I feel like it's
Very
better to understand this is actually we use this tool is more for treatments, like accuracy.
Like
So for example,
measurements.
if like today you wanted to develop like a cure for curing cancer, right? For example, first of all, you want to have a high sensitivity because you want to make sure that your treatment can cure the cancer cell, like the cancer cell. But another thing is that specificity, you also want it to be high, because you don't want your treatment or the medicine to kill the healthy cell, right? Because if they're targeting the healthy cell, that is a specificity, which means they're not predicting the cancer cell, they're predicting the healthy cell.
yeah.
And if you have like a low specificity, so your medicine probably, you don't know your medicine whether it's going to kill the healthy cell other than the cancer cells. You want to make sure you also have a high specificity So you know that medicine, like the medicine, how much time it's going to targeting on a healthy cell.
So for sensitivity, it would be the ability to detect if they have cancer. So
Exactly.
7% chance they have cancer.
Yep.
But let's say for specificity, we want to be able to guarantee within 90% that they don't have cancer.
Exactly, that's
Okay.
right. Yeah, so that's how they work with each other.
That's
Yeah.
great.
So that's why you want both of them to be high. So actually, that's how the ROC curve was introduced.
Okay.
You still remember ROC curve?
No.
No?
It sounds
Like
familiar, but I
briefly.
don't know what it is.
Yeah, so on the ROC curve, it's like this. So this one is a sensitivity, right? The higher the better, because you can accurately target it. But like this is 1 minus specificity.
What, at the end or the whole bottom?
Oh, in the x-axis.
Okay.
So the y-axis is sensitivity. And the x-axis is 1 minus specificity. So you want the 1 minus specificity to be very small, right? That means your specificity is very high.
Yeah, we want a high specificity.
Yeah, so you want this one small and you want this one to be as high as possible. So that's why you see we have a balance point right here, kind of like right here, because if it keep increasing, your sensitivity is not going to change.
Yeah.
But your specificity is going to get like lower and lower, which is going to be horrible. Yeah, so that's why you see we always find the balance point to have high enough sensitivity and high enough specificity to have the best treatment, on your pretty much disease or anything. Yeah. So this curve is called like ROC curve. Yeah, I mean it's not on the COM packet. I don't think so.
But it might be on the comp because this. I remember this.
Yeah.
Yeah, and they covered this in a couple different classes too.
Okay.
Yeah.
Measurements and stuff.
Yeah, but because they talk about it under logistic regression, it's related to this classification because you're talking about you accurately predicting the outcome. So, yeah, but it's not really like a huge section because beyond this, they didn't talk about it anywhere else. Yeah, beyond in the logistic regression section.
Okay.
Yeah, but you understand it now?
Yeah, definitely.
Cool.
Very good.
Yeah.
Perfect.
Yeah, I'm good.
And if you go like page 78, so pretty much actually this is supposed to be all for logistic regression. But if you go page 78, there's a review again from that Chantelli guy, whatever they called it.
I don't know.
Yeah. It's on page 78 in the middle. They talk about logistic concept list. So over there, let this up. Talk about some like additional terms in the logistic regression, actually, which is not as important as the terms we just discussed, but because they're in the package, so it's no harm to talk about them. So the first one is a WALD statistics. Actually, the WALD statistics, WALD is like the it's actually another type of a regression weight. I think this one is the standardized regression weight. But the thing is that, because remember, again, our outcome is a categories. So we don't technically have a variance of the outcome. So technically, if you don't have a variance, how could you get like a standardized score, right? That's why they say this WALD statistics is danger. If you use it, it could be possibly inflated due to large betas and excessively large standard errors, because the thing is that we only have two outcomes. We don't have a score change. So that's why WALD statistics is like rarely used or discussed in the logistic regression. I mean, some scholars or researchers, they talk about it, but I think based on COM, they don't want you to use it.
Too much.
Yeah, because it like kind of could jeopardize the results of the logistic regression. So they rarely use that statistic to talk about if the WALD means anything of the results to your logistic regression.
What page do you want to remind me?
78. It's like in the middle. They just put these additional things up there,
Okay.
which I don't really see necessity.
Mm.
And the next one is this log likelihood ratio test. That one is the same as -2 log likelihood. So it's exactly the same thing. They just call it a little bit differently. And the next one is a classification table, which we already covered. But here they said it's a 2x2 table, the rates and misses. Yeah. So I think that's what Rachel said. So what they do is like they do like this. But when they do the hits and misses, they're kind of like doing it differently. So 2 by 2. So pretty much this means that this is your yes, and that's your no. And that's yes, and that's no. Yeah. So when they're doing that, they have numbers here. So you're gonna look at, so this one is gonna be like predicted yes and predicted no. And this is your observed yes and observed no. So that's
observed means what actually happens.
Yeah, and predicted is what like the theory or whatever
what we
trying to do it.
Yeah, this is the box that I was remembering.
Yeah,
And
so
this is important. This will be on the test for sure.
Yeah, that's why they're doing the hits and misses. So they see how much they could really hit, you know. So they're trying to match you, like how much time when you observe it's also, you know, predicted going to happen. Yeah. So that's why they do the hits and misses, and they use this information to calculate the classification table.
Okay.
And the next one they call this Cohen-Kappa, which is actually a little bit weird because it's a type of a reliability testing. And I don't know why they included up there. They said it's agreement statistic that corrects for chance agreement. Because how they do Cohen-Kappa is actually they base on the correlation, and they look at if your agreement is highly correlated with, you know, your correct for. Oh, hold on. How do I say that? They look at the correlation between. I don't know. I don't think. Okay, they say this. They said agreement statistic independent of chance agreement. So they want a high percent of agreement, bigger than agreement. Okay, I don't like the way they said. I don't really know if they say it right or wrong. Because the way we're going to talk about Cohen-Kappa is under the reliability testing. I don't know why they put up there. Because again, they grab this list from that Chantelli, that little, you know, person's name they coded. So it's not really under the student's packet. It's just something else they copy from other books or whatever. So, and hit rate is whatever the rate that we calculate here from the classification table. So that's what hit rate means. So that means the percentages we correctly classify the variables.
So we could use that for any of the hit box.
Yeah, exactly. So that's why
the hit rate could be for any of the 4 boxes.
Yeah, so that's the number of this and plus the number of here and divided by the total of it. So you get the hit rate. Yeah.
Because I bet we're gonna have to calculate this crap.
Yeah, so let's just say if we have a 10 here, 20 here, and this one we could have, I have to make sure, that's 10, 10. And this one means we have 20 no observed. This one could be like 15. And that one could be 5. Yeah, so when you calculate the hit rate, you just use 10 plus 20 divided by plus
30%.
Right?
33, officially, right? That's 30.
Is that right?
I'm confused now.
Oh, yeah.
How do you calculate it? We're 10 plus 20.
Yeah, because that's your hit rate, right?
Okay.
If your observed is the same as predicted, right?
Right.
Observed is yes, they also predict as yes, there's a 10th though. And this one you observe as no as 20, and you also predicted no as you know, the same. So that's 20 of them. You add them up and divide it by the total, total chance. Yeah.
So you add them up and then
divide by the total 4 numbers of this.
Oh.
Yeah.
So that'd be a 60%.
Yeah, but actually it's supposed to be 100, so that's why I make up a number wrong. Yeah, but that's how you calculate it.
Okay.
Yeah, these ones, the bottom number always be 100. Yeah,
And that would be our specificity.
This is your sensitivity.
That's what I mean, sensitivity.
Yeah, that's how you actually hit.
Specificity would be the no.
Yeah, the specificity will be these 2 add up. So that would be 20 divided by 100. Yeah.
Yeah, this is the box.
You have it.
Yeah, I found it. And so that helped me. That helped me understand it a little bit more.
This is money.
And then it also includes like type 1 and type 2.
Yeah, specificity. I thought specificity is supposed to be 1 minus this.
I don't know what the formulas and calculations are if you would need to calculate a hit rate, but That's the box that helps me understand specificity
No,
and sensitivity. And,
Perfect.
yeah. Yeah.
Good job. Thank you,
Thanks.
Rachel, for sharing.
Thanks. Yeah. I had it somewhere.
Okay, good? Okay, good. So, and then if we continue with the rest of the part, they talk about the assumptions at the end. And then talk about what's the difference between logistic versus discriminant.
We did that already.
Yeah, but they don't really have any, it's more like a theoretical talking. And the last part is this odds ratio.
That will be on the test, I believe.
So actually, odds ratio is like expected B. Yeah, that's what odds ratio is. So that's why you calculate this number to see how much chance that one category could be happening with the predictor changing or increasing.
Can you show us how to do odds ratio?
Oh, that's what I'm saying, it's that little formula, you have to use the predicted probability to do it.
Okay.
You have to calculate the, okay, so first of all,
So you're gonna show us.
I don't think it's really, they're gonna ask
So,
you
so
guys-
for expected B, the odds ratio would be 10 to 1, right?
Yeah,
Just for
odds
every,
ratio, yeah,
just for every one we increase, it's increased by 10 times.
Yes, exactly, yeah.
Okay.
Can you explain that to me?
Oh no, I can do it here. So
Okay.
for example, let's just say if we see whether we can do male and female on getting married.
Getting married or finding a mistress, right? They told me male mistress.
A mister.
Have affair.
Really? Male mister.
Okay, let's do male. So let's just say gender is a predictor, and we want to predicting their marriage rate to see which gender had a higher chance to get married before they turn into 30. We can do marriage before 30. Okay. So let's just say for male, if they are married, so we're gonna use a yes as married and no as no married, okay? Yes and no. So for example, let's just say we collect a bunch of people and find out like for male, there's like 20 of them, they say yes, but for female there's like 10. And for no marriage, there's like maybe a little bit, maybe 5. I'll make it easier for calculation. And for female, there's like 8 of them. Oh my god, so maybe 15, yeah. So total, we have a 25 male and then 25 female. So total, we have like 50 subjects, right? So to calculate actually the odds ratio is very easy actually. So first of all, you need to calculate how many percentages that male get married from their group, and also how many percentages that male didn't get married in their male group. So to do that, you just simply use 20 divided by 20 plus 5. So that's the probability of how male getting married, right? That one is, I need my math.
Big brain.
How much is it?
20 over 25?
Yeah, it's 4 over 5. Can I use just
80%.
fractions? Can I just use fractions? Make it easier?
Yeah.
Okay, thank you.
That's 80%.
That's 80%?
Yeah.
You sure?
Uh-huh.
I want to use this. It's easier for you, actually. Okay, I'll go 80%.
Yeah,
I
pretty
trust
close.
you. My brain doesn't work on maths today. Usually I'm okay.
My brain doesn't work on that.
So this is for male. What's the chance of male getting married? For 30. Okay. So that's the first step. And the second, you need to calculate what's the chance of male not getting married only in the male group. So that will be 5 divided by 20 plus 5.
25?
Yeah, so that's going to be 20%. Because when you add this one up, they're going to be equals to 100%.
Yeah, 1/5.
Yeah. So that one is, so this one is a male not getting married, the percentages of not getting married.
Yeah, makes sense.
So it's just out of the males.
Yeah, you only look at the male itself,
Oh.
not the outcome. Yeah,
With
And
the
then-
odds ratio.
exactly. No, not yet. This is not odds ratio.
What is this?
I'm just, because you want me to show you how to do it. That's one thing. It's easy, but it's just procedures.
Okay.
So after you're done for male, then you do the same thing for female, right? So you do their, how much percentage they get married. So it's going to be 10 divided by 10 plus 15. Eric.
Number 15?
Uh-huh.
It's
That'll be-
33%.
2, yeah.
2/5? Wait. Oh,
It's
10 over
250.
25?
How much? It's 2 over 5.
Let me get one. Sorry.
It's 40%.
It's 40%.
I know it. I just. Anyway. So that's female getting
You're
married.
telling Rich.
Sorry, I'm manipulating my mentees.
I feel abused.
And then you do the same thing. You go for the female, the chance of not getting married. So that would be the 50, divided by the total number of females. And that's the 60%. Because when you add them up, there's going to be 100%, right? So that's female, not married. Right?
There's a lot more females getting married. And there's a lot more males getting married. That's weird.
It is. Huh? So the next thing to calculate the odds ratio.
For America, that'd be weird. I guess other countries would be the opposite.
Yeah. Actually, I do this before is because I want to show you how this compose and you can understand the term. But technically, to calculate the odds ratio, you don't have to calculate them all. But because I do all of them, so you can understand I'm not really jumping, Actually, to calculate that, you just simply, you do need to calculate them all. So actually, the next step, you have to calculate what's the ratio or the odds only for male that they're getting married. So to do that is actually you're going to use male getting married, which is 80%, divided by,
100.
so yeah, they're getting
So what
married.
is the 80% called? Is that the probability?
Yeah, that's the probability or the chance of male getting married.
Chance or probability?
Yeah, among the
okay,
male,
which is
among
different
males.
than odds.
Yeah, it's different than
Okay.
odds. Yeah. So that's how you calculate, this is the odds for male getting married in the male group. So this is the odds, only for male. So you're doing the 80% divided by 20, and you get 4. And the next, so that's for the odds for male only. And the next, you do the same thing for female. So you use 40% divided by 60%. You get how much, Eric?
80?
It's 2 over 3.
Is it?
Yeah.
2 over 3 would be 66%.
Yeah.
66.6.
Okay, I'll go 67.
67.
Yeah. So this is the odds for female to get married. Okay, and then lastly, you're gonna do this. Because this one you only look at the male odds. This one you only look at the female odds. Now you need to look at overall odds. So that is the odds ratio. You need to calculate.
Oh.
So now you really get calculating the odds ratio. So because let's just say we set female as reference category because we always put the reference category odds at bottom. So if we use a female, that's going to be 67%, and that's male, at 4. And whatever you add up here is the odds ratio you're going to report. That's how you calculate it by hand. But I mean, it's easy. If you have the numbers, you just do it, but it just not necessarily going to be on the comp. I don't think it's going to be on the comp,
No?
honestly.
Okay.
Yeah. They're probably just going to give you the odds ratio, or they give you this. They tell you the odds ratio for one group, the odds ratio for another group, and what is the overall odds ratio.
Okay.
Yeah.
So to get the odds ratio, you take the percentages, the probability percentages.
Yeah.
1
First
over
of
the
all,
other.
yeah, you have to calculate each of the group, but just by themselves.
Yeah.
Okay.
You have to look at the male, get married, not get married, and the female get married, female not get married, and get their own group odds ratio first. And then you get overall odds ratio for the outcome.
So according to this, men are 600% more likely, almost 6 times more likely to get married than female.
Yeah, exactly. Which is actually doesn't make any sense, right?
But we can also put female over male, right?
Yeah, but that's one. So whatever number for the bottom is your it has to be a reference category. Yeah, that means.
How do we know the females are the reference category, not the males?
Oh, it's pretty much based on the research purpose. Like it depends on you can set male as reference. I'm just saying.
For whatever.
Oh, yeah, you always put a reference group. Yeah, if you talk like this, you're just gonna talk about how much more likely male. If you put a female us, it's gonna be how much less likely female, right? Yeah. not even say or discuss the
So
results.
females would only have a 17% chance of being married compared to a man.
Yeah, even look at data here, you can see
Yeah,
that
you can
male
see.
is definitely more higher to get married than female.
I don't ever want to get married.
Yeah,
That's not true.
that's true. Yeah, before 30 at least. Yeah, so but remember, this is exactly, the odds ratio is the same as expected B. So SKSS will calculate it, so usually that's why we don't really do this ahead calculation these days.
Okay.
That's what odds ratio is. And that's everything for logistic and discriminant, I would say, regression. Yeah. Any questions?
My brain's just trying to catch up really quick. I remember doing this, and it's very
Uh-huh.
simple. It's kind of
Yeah,
lengthy,
it's not
but
hard. Because remember, you're
Right.
just trying to predict which probability could which category will likely to happen over than the other one.
right.
Yeah.
So okay.
Yep. I thought we could go through decision tree today. I keep overestimating my group.
Oh.
Because we're supposed to cover this yesterday.
Yesterday.
Mhm.
We'll have to have an extra session on Tuesday.
I know, now I'm really worried because we may not able, because we still have like, factor analysis, decision tree, reliability, validity, and external validity.
Can we do an extra session on
Item
Tuesday?
analysis. We have so many things we have to talk about. I know.
Can we do an extra session on Tuesday?
I work on Tuesday.
I hope like Monday at least we can, Yeah, the thing that also I don't want to go too much detail because, the con we're gonna cover everything.
Yeah.
I don't want, focus on too much on one thing and miss the other part.
Mhm.
Okay, so next one we're gonna go for path analysis. I mean, thank God they don't have that much for path analysis in this. SEM represents for structural equation modeling, and pages we're on is 65 to 66 and 72 to 73.
SEM is structural equation modeling.
Yes. Yeah, if you look at the packet, they have the whole name on it.
I'm just making sure.
No problem. Okay, so first of all, path analysis is actually, it's about building also a causal model. And actually, it's kind of like to go beyond, is actually we're trying to build a theory. Which means this model always works, no matter what kind of data you have, no matter what kind of occasion you're looking. It's like you're building up a theory. That's what path analysis do. So that's why it's beyond multiple or beyond the regression analysis building. So in path analysis, remember we don't talk about predictor or outcome. We're talking about exogenous variable and endogenous variable.
So no predictors?
Yeah, there's no predictor or outcome. We just call them exogenous or endogenous.
Okay.
And a basic model is like this. Remember we go through that and ask you guys how to define a. I don't remember that.
So A would be exogenous, right?
Yep.
Because nothing's poking in it. Everything else would be endogenous because it has something poking in its back.
Yeah. So on the packet, they also talk about how you tell the difference between exogenous and endogenous. So here, A is the only exogenous, and all the rest are endogenous.
Right, does that make sense?
Mm-mm. Tell me one more time.
So if you have an arrow poking in your back,
Okay.
you're indo. If
Okay.
you have something inside you.
Okay.
And if you don't have anything poking in you, you're only poking at other things, then you're exo.
Okay.
It's your
Yeah.
poker versus a pokey.
Perfect.
I like that.
That's good.
Yeah, actually.
That's really good. And I have a little visual with arrows here to help me.
Let's see. So on the
It's
packet,
like the big spin roll spin prison.
And no
Yeah.
accent.
on the
Okay.
packet, they explain that in two different. So on the page 66, the way they explain it is okay. On page 68, they explain endogenous versus exogenous, but instead they say exogenous is like predictor. I mean, you can see as a predictor because you always use that to predict all the other things.
Yeah, it's never predicted.
Yeah, but endogenous could be outcome, could be mediator, could be moderator. So on page 72 and 73, they have a better definition of endogenous and exogenous.
Okay.
This is like pretty much what the path analysis or SEM looks like.
Uh-huh.
Because remember in regression you don't have these crazy relationships. Yeah, you just have one straight line. So that's why you see you're building a theory. You're trying to see internally how these things are related with each other. Yeah, cause to each other. So usually in path analysis SEM, the packet didn't go further because these analyses are very complicated. So you don't even have to know how to do it in detail. Yeah, you just need to understand a little bit conceptually. So we're not going to talk about assumptions, or whatever. Even though they do have assumptions, I think there's like 10 of them.
Okay. Cool.
Yeah, because I do a structural equation modeling for my dissertation.
Oh, you did?
Yeah, which is not a wise choice to do.
But you finished it.
I know, but still, I so hope I didn't do it. It's so much pain.
Pain causes pain is weakness leaving the body.
Next, I'm going to talk about
In theory, at school.
recursive versus non-recursive. Recursive is the arrows to the right. Yeah.
Recursive.
So recursive is like this. If you have an exogenous variable, right, you go to your endogenous. This is recursive. But if you have like this, that is non-recursive. That means your exogenous is kind of impacting the endogenous, but endogenous on the other way around could also have a feedback on your exogenous variable. So that is non-recursive. Impact and feedback.
Wait, that example is non-recursive?
Yeah. So this is a non-recursive.
If you
have just one straight arrow, you just have
recursive.
a, yeah.
Oh, I had that backwards in my head. Because recursive usually means,
I know, but if you look at the packet,
Well,
hold on. I hope I didn't mess it up. My brain doesn't work.
No, I think you're right.
Yeah, I'm right.
what page?
It's on page 72.
Okay.
So that's why path analysis and SEM is based on recursive model. If you have a non-recursive model, you cannot do a path analysis or SEM.
Oh, so it's recursive versus non-recursive model.
Yeah.
So it has to be recursive.
Yeah, because causal model could be like this. But if you want to do path analysis for SEM, you cannot do non-recursive model because they are built, their stats rationale is behind the recursive model.
Roger that.
Yeah, this one, they have like a different technology to do. Yeah, because this kind of causal model, you can still do it. But you're not going to do it using path analysis for SEM.
So the top one is recursive.
Yes.
Non-recursive.
Oh.
Yeah. This
And
one.
it's built on.
This one, no, path analysis and SEM is built upon recursive model.
Okay.
So that's why if you have this kind of model, you can use a path analysis SEM to talk about it. I mean, you can also have this model, which is non-recursive model, but you cannot use path analysis SEM to analyze it. Yeah.
Can't use.
Yeah, you can. Yeah.
So for path analysis and SEM, you have to have recursive.
Yeah, you have to have a recursive causal model.
Recursive causal model.
The next thing is we're going to talk about a bunch of like effects. So effects actually is really like coefficient, like how the exogenous is affecting or predicting the endogenous variables. So there's like 4 type of effects in the path analysis for SEM. There's a direct effect. There's an indirect effect. is Spurrier's effect.
See, I remember these because of all the visuals.
Yep, exactly. That's what I'm gonna also use to
That's the only thing I
explain.
remember about stats. If there are pictures, I will remember.
And there's also unanalyzed.
Unanalyzed?
Yeah, unanalyzed.
So there's 4?
Yeah, there's the 4 different effects. And they are discussed on page 65. They're also on page 73. So they're exactly the same thing. But they just tuck them in 2 places again. Okay. So direct effect is like this. You just have A cos B, so that's direct effect. So in this chart, we have like we have 1, 2. Yeah, we have just 2 direct effects. So from D to E and C to E. Yeah. So make sure you have so A only have 1 arrow pointing to a second variable.
How come it wouldn't be a direct effect between A and D?
Because see, A is not going to not only go to D, it also goes to C and B.
Oh,
yeah,
so if it has more than
you have to have only like one
arrow leaving.
Yeah.
Okay.
So CE
So one-
would be a direct effect.
Yeah, so DE and CE, these 2 are the direct effects.
Okay.
Yeah. And the next one is indirect effect. It's like this. Let's go from A to B and to C. So from A and C, you have an indirect effect.
So like from B to E?
Yeah, so like B to C. So between B and E, you have an indirect effect.
So B affects E indirectly.
Yeah, exactly. Through C. Yeah.
Got it.
And the Spurrier's effect is like this. So you have A goes to B, goes to C, and goes to E, goes to D. So this is Spurrier's effect. So you have one thing cause the other things at the same time. So here, A to D, C, B, they are Spurrier's effects.
So the indirect effect would be, on this one would be like A to E, would be indirect, right?
Correct.
Yeah, or like a B to E.
B to E,
Yeah.
those will all be indirect.
Or even an A
A to
to
C.
E through C.
Yeah.
A to C?
A to E through either D or through C.
Yeah, because see, A through B goes to C.
Yeah.
Yeah.
Okay.
Yeah.
So yeah, the interesting is that because if you look at here, it's hard to tell whether between A and C is a direct effect or indirect effect because A goes directly to C. But A also indirectly goes to B and goes to C.
Yeah.
So that's why under these kind of cases, if they have like a Spurrier's effect, we don't really discuss their direct or indirect effects because it's going to be confusing, right?
Yeah.
So what would be a spirit? A would be a
Spirit.
Yeah. So we'd rather say that A has a Spurrier's effect to B, C, and D.
Okay.
So instead of to say that A has a direct or indirect to C, right? Because it's confusing. Because if you look at A and C, they do have a direct effect, but they also have an indirect effect through B.
Okay.
Yeah.
So in that case, Spurrier's effect is more accurate. Discusses. And the last one is unanalyzed effect. It's like this. You have both A and B. They're maybe predicting they're actually going the same thing or going different things, but they're not pointing to each other. Actually, in our case, we don't have it because we don't have a second variable. We don't have unanalyzed effect here.
Say it again. So an unanalyzed effect is when they don't have.
Between A and B. They don't have arrows
Oh,
pointing
nothing.
to each other. Yeah.
But they're both affecting the same thing.
Yeah, they could be both affecting the same thing or they're affecting different things. So that's why
So-
in our case we don't have it because we only have. Remember, okay, another thing that unanalyzed effect is between exogenous variables.
Okay.
It only
Oh.
exists between exogenous variables. Yeah. If you have one exogenous variable, of course there's no unanalyzed effect because they're not pointing, right, influencing or related with
Only.
only between
So-
exogenous
So we can
variables.
say there's an analyzed effect between A and B.
Yeah.
And what if you erase the line that goes from B to C?
Oh, it doesn't matter. It could be like this.
So there's still an analyze effect now?
Yeah, but you have to make sure they're in the same model. Because
Yeah.
like this, it seems like they're in two models because they're not related.
And what if C
Oh,
and
I
D
know.
affected?
Oh yeah, if you do like this, yeah, it's the same. Still A and B, they're unanalyzed effects.
Okay.
Yeah,
Roger.
as long as they're not affecting. So that's why it's come from exogenous variable effect.
Thank you.
So, can we go back to the spurious?
Uh-huh.
So, in the example over here, A is spuriously.
They have a
Direct
spurious effect
effect.
to B, C, and D.
Okay.
That means you have one variable causing or relating to like different variables at one time.
Because I thought I remember it was like B was spuriously related to D. Because A was
Causing them together?
causing both of them.
I don't know. I mean, the package didn't say it.
Say that again, right?
In the example over on the right,
Mm-hmm.
so A leads to B, C, and D.
Yeah.
B is spuriously related to C.
Yeah.
Right?
That sounds right.
That's what I remember, is like to go kind of backwards and then.
It's not necessarily because look at our chart here. Like B has nothing to do with D, but B is the spurious effect from A because A caused D, caused C, caused B.
So
B
is
has nothing to
so
do.
can you say that D is spuriously
No, we say A has spurious effect on
Effect.
B, C, D because
Okay.
A caused B, caused C, and caused D at the same time.
okay.
Well, no. So you could say B and D are spuriously related.
Related but not effect.
That's what it says here for
Yeah, that's what I
73,
thought
number
it
6.
said.
Oh really?
Yeah,
So-
you could say they're related but not
So it says
affected.
spurious effects is when two variables have a common cause.
Yeah. Represented by.
Yeah, that's what I thought
No.
it was.
They have a common cause doesn't mean that they're related. It just means they have a common cause of A, but that's it.
Yeah. So
They
you'd
didn't, they
say,
didn't say like, okay, these two variables are related.
but
They just say A caused both B and D and C.
Yeah. So I guess if
did
you're
you
talking
say
about
B and D are spuriously related.
if you're talking about them being related, yeah, I think you can say that. But if you're talking about them affecting or causing, then no, it would be A is spuriously affecting.
But the thing is that if, I mean,
I remember that from class.
I don't really,
No.
because these two can be two different things. They can be not related.
Yeah, but they are related. They're related through A. I mean, from the picture.
No, like A caused them. Like A is the reason why they're happening.
Mm-hmm.
But if D like to say if D happens, it may not necessarily say that A will happen. Because A caused them, not D caused A.
Yeah, but
When you
if you're
say related, it means that they could be causing each other. They could be related with each other.
no, in my mind, I'm thinking of the word related, like no causal effect, just relate, like
Just
just like
association.
association. Yeah,
Yeah,
so
but still like it's
spuriously associated through A or
I'm looking
something.
it up.
I don't know if it is even a big deal or not, but I think I remember Dallenberg
They
saying
say that.
that. Yeah, yeah.
I mean, when I learned SEM, from that class, like we never learn like they have to be, related or spiritually
Yeah,
related.
But it's important for me to know also that A spuriously affects D, C, and D. Because if you're talking about the cause, then absolutely A is the cause.
Yeah, but doesn't mean that BCD has to be, because this one could be age,
Mm,
that one could be like GPA. GPA has nothing to do with age. I don't
Yeah.
know.
that's okay.
Yeah, I mean, okay, whatever, like maybe whatever like your professor told you, because I never learned it. I mean, I just know like A caused them.
Yeah.
I mean, not related.
Okay.
Yeah, and on the packet, they don't really say it. Like, they just say, on page 65, they say spurious means one variable caused two different variables. Or three more variables.
Did they just talk about cause?
Yeah, and on page 73, they just say that when two variables have a common cause.
Okay.
Yeah,
Alright.
and that's it.
Well, that's simple enough. We can move on. I
Yeah,
think.
okay. Yeah, but if packet says that, then maybe you just go for whatever the professor said. If they have options for you to choose, say whether A and B is spuriously related, yeah, you just check that.
Yeah.
Choose that
If that's
option.
an option.
Yeah.
I
That's
can't
an
find a
option.
good
It's a multiple
example.
choice.
Yep.
So
Yeah, I don't. I thought that was on one of her tests. But my memory is not the best, so maybe I'm not.
Oh, don't worry.
Okay.
Yeah, and that's all you need to know for path analysis and SEM.
Cool.
Too detailed.
Yeah, there's really nothing more. Any questions?
No.
Okay, good. The last analysis that we always do, well, not last, but because there's supposed to be two of them, but like the last analysis, like the last, it's not really like a statistical parametric analysis. It's a little bit different. So, but like at least it's still like a parametric test that we do. Is path analysis. Oh, sorry, factor analysis. What am I talking?
Factor analysis.
I'm sorry, guys. No, pass. We already finished pass. It's factor analysis. That one is from page 74 to page 77. Okay, so path analysis. Oh, sorry, factor analysis. Factor analysis. So it's a very different analysis than regression or t-test. We're trying to compare group differences. So actually, this type of analysis is we're trying to. I'm just gonna say define and purify. Organize.
Organize. Yeah.
I like that word. Define and organize dimensions or factors from a set of items.
Okay.
So that's what factor analysis do. It's not really giving you let you to do a relationship, right? Predicting, that's what regression we talk about, or path analysis, or it's not comparing group differences.
So it's clustering all the similarities together.
Exactly. Yeah.
Okay.
Perfect job. Yeah.
Thanks.
So I think on page 74 they have like a better definition of what is factor analysis.
Is there a visual for this?
Well, you can see a visual is more like this. Like usually we use factor analysis for like a psychometric test. Like just say if you have like a BDI, inventory, and you have like maybe 100 questions of it, and you're trying to categorize how many dimensions or factors we can extract it from those 100 questions. So for example, you maybe out of the BDI you're more focusing on a certain aspects you wanted to study. You don't really care about that maybe the your subjects personal depression or work depression, because there's a personal depression, work depression, emotional depression, physical depression, whatever. But you only want to focus on certain dimensions or aspects that you want to analyzing on. That's why you need to use a factor analysis to find out of these 100 questions, which ones are measuring their emotional depression, which ones are measuring their work depression, things like that. So we need to use a factor analysis to help us to identify those dimensions or categories or factors. Yeah.
Okay.
So yeah, that's pretty much the most common use of factor analysis.
Yeah, factor analysis is cool. I like factor analysis.
Yeah, I do too.
Good. Yeah, because it's more like psychological oriented test.
Yeah.
It's not really like lots of the stats reason behind it.
Yeah. Well, that's a lot of what psychologists do. Is they're trying to categorize and to diagnose and to identify different personalities and.
Yep, that's right.
Yeah.
Okay, so in factor analysis, the first thing is we have to identify the type. So there's usually 3 types. The first one is called the principal. I should write out the whole thing. Principal component analysis. And the second one is called exploratory factor analysis. The third one is called confirmatory factor analysis. Yeah, each of them is supposed to have analysis. Just lazy everything. Sorry.
I would do the same thing as you.
But I can put up their abbreviation. So this one is a PCA for principal, and EFA for exploratory, CFA is for confirmatory. PCA, yeah, I can do that. So on page 74, they have the definition of these three different factor analysis. But I will just briefly talk about what are the differences between them. So principal component is kind of like always the first factor analysis we do. Is we're trying to extract as much as factors or dimensions out of the whole question set that we want to look at. So this one is like a draft. You want to see that? Like you just draw a draft to see how many factors or dimensions we could pull out, or categories from those inventories or test sets.
A draft to pull out just to see how many factors
possible,
might.
yeah.
Oh, okay.
Yeah, exactly. How many dimensions, factors or aspects we can pull out from like a certain, set of tests or set of questions.
Okay.
Yeah. Second one, the exploratory factor analysis is usually it could be like as the next following one after the draft. So this one, when we do like an exploratory factor, we're trying to like purify. This one is pretty much where we're trying to purify which of the factors or dimensions we want to study on, or we're more interested into, right? Because once you analyze your data, your participants may not give you certain information for those dimensions, for some of the dimensional factors. Therefore, you only need to be able to analyze the factors and dimensions that your participants will be more into. So that's when we do an EFA or exploratory factor analysis.
So it's
purify the dimensions.
It's to only use certain factors?
Yeah, most of the cases. Yeah, you only focus on certain dimensions of factors.
So it's like these other dimensions aren't really worth it, let's throw them out.
Yeah.
Oh.
So it's like we start out with 12 things, and really the extra, these extra 4 only account for, a small percentage of our variance. So we're going to throw them out
It's
and really
like-
just focus on these big 8 ones.
That's right there.
So
Yeah, principle
the
is
draft
all
will
you
pull
look at
out
100. Yeah, it's all you look at all
like
the
12.
questions.
Like everything.
For example,
Yeah.
let's say the draft. So you always do all 3 of these. First you do the PCA and then you do the.
No. It's dependent on your research purpose. If you still wanted to look at every dimensions, you just do
But
PCA.
let's say if
Oh,
you
I
do the
see,
principal
okay.
component, there's
Yeah.
100 dimensions
Oh, okay.
that add to your thing.
Yeah.
But when you do exploratory factors, let's say 10 of them explain 90% of your variance. So the extra 10% for 90 factors isn't worth it, it's crap. It just makes it messier. So let's throw
okay.
that out. Let's focus just on these 10 because they represent the bulk
90%
majority.
of the
Yeah.
variance. Okay.
Yeah. Principal component always like 100% variance.
Yeah.
Representation.
Oh, okay. Alright.
So it's like, well, how do we get the most bang for our buck? Let's focus on those ones. And at a certain point, you say, it's not worth adding these extra components in. There's
Yeah.
too much.
Yeah, so that's why EFA is usually like when you have your data, like once you have your data, you start analyzing, you'd be more like to use the EFA rather than PCA.
Yeah, I remember the stats pronounced for this.
Yeah, I
Mhm.
remember vaguely trying to
There's like kind of cutoff
figure
point.
out. Yeah, the cutoff point, and then. Okay.
And confirmatory, I don't know what that is.
Yeah, confirmatory is actually it's more like advanced. Advanced. So confirmatory usually after following the EFA. If you do a EFA, usually you have to do a CFA. Because we do a confirmatory factor analysis, that's why it's called confirm, because after we purify to find out, okay, which factors are matters, and the next thing is that we have to like validate them. So it's more like a validate your factors or dimensions.
Okay. Roger that.
So that's why it's like advanced. You keep going, explore these factors and dimensions.
And then you confirm and validate.
Yep.
Cool.
And that's the 3 types of them, and it's on page 74.
That's one of the few pages that I don't have.
Oh, you don't have?
No, I have 72, I think it was 75, I forgot that.
Oh,
That's
it's
okay.
fine, yeah. So one thing for factor analysis is we don't have assumptions. So we don't need to check assumptions at all. Because remember, they're based on questions. And your questions are Likert scale.
Yeah.
So technically the score has a limited range, right?
Yep.
Yeah. So you could easily avoid it because you're not really doing like you're not trying to tell significance actually when you do factor analysis. You're not testing any hypothesis. You're just trying to categorize, your big groups into like these different sections and dimensions.
Makes sense.
Yeah, you're kind of like clustering your people. I mean,
You create an organization.
Yeah, so you're not really testing significance. So
No.
that's why you don't need assumptions. Okay, so that's why we're just gonna talk about like the key terms when you do a factor analysis. What do you need to understand so you can analyze the results. So the first one is factor loading. So factor loading is like it's like correlation coefficient. It talks about the correlation between each of your item with your factor. That's with R. So you're just gonna look at how much that item is gonna explain that specific factor. Yeah, so that's factor loading. So that's why it's like the correlation coefficient. Yeah, how each of item correlated with your factor. So that's why when you do factor analysis, they create a correlation matrix, but that correlation matrix is between items and items.
So the items correlate the factor.
Yeah, but this one is talk about how item is correlated with that certain factor.
Yep.
Yeah.
So they could have a strong correlation or they could have a weak correlation
Yes.
even though they're still part of the factor?
Yeah, exactly.
Okay.
Yeah. So it's like another thing to do. So this one you can see as like a predictor outcome. You can see which item is highly explaining the factor or which ones are not.
Or not really, but they're still included even though
Exactly.
they have. Okay.
Yeah. That one is also on page 75. And the next term is communalities.
Commonality?
Yeah, communalities. Sorry.
It's okay.
I cannot speak English anymore. Communalities.
Communalities.
Commonality? Communality.
No, commonalities. I'm just.
Actually, this one is highly related with factor loading. So this one just communalities is telling you how much of the item has been used of that factor, of that certain factor. So which means if you have a low communality, also means you have a low factor loading. If you have a high communality, that means you have a high factor loading. And pretty much these communalities also not only talk about item to one factor, it's kind of like talk about items to all factors. So if you have one item, it's kind of like combine all the like little r's to like different factors. So for example, there's a factor 1, item 1 has a correlation with factor loading. There's like factor 2, right?
To see how one item correlates with all the rest of the items?
Yeah, so that's the total. So that's what we call communalities. It's kind of like have a combination of all the factor loadings from one item to all the factors. Yeah.
Okay, so.
Yeah, so you can see some of the R could be 0, some of the R could be bigger, some of the R could be like smaller, based on which factors that item was explaining to. Because remember, when we do factor analysis, all the items they're measuring the same thing, right?
Yeah.
So that means you're definitely gonna measure all the factors possibly. It just depends on which factor you could possibly measure more or measure less. Yeah.
This is how they define.
Yeah, that's how they define. Yeah, that's how they
right?
define the factors. Yeah,
Yep.
by looking at
Wow.
items gonna highly loaded on that factor.
Right,
compared
right.
to loaded on other factors, right? Yeah.
Yeah. Huh, that's very interesting.
Okay, I'm gonna do it here. Let's do the bottom. So the next term is rotation. Oh, I should not do rotation. I should do not because I put rotation there. Okay, next is eigenvalue.
eigenvalue.
Thank you.
That's what I remember.
I always call it eigenvalue. Yeah. Eigenvalue is on page 76.
We're not talking about factor rotation, we're doing that later.
No, we should do that later
Okay.
because I'm
That's
following
fine.
the procedure. Yeah.
Okay.
Like the packet is so not well organized. Eigenvalue is actually related to total variance of the all the factors. Let me explain. So to determine the eigenvalue, we always want it to be bigger than 1 to extract number of factors or dimensions. So we always to see how many number of factors we should be extracting, from that set of items or set of questions, we use the rule of eigenvalue for that factor has to be bigger than 1.
It has to be bigger than 1.
Yeah.
So to keep it as a factor?
To count it as like one of the factors that we decided to extract it from that set of questions. So usually, we use like a script plot, right, to show the eigenvalue, like graphically. So like remember we do this, right? Yeah. So these are the number of factors. So for example, I have 1, 2, 3, 4, 5, 6, 7.
Script plot?
Yes, called script plot. That's the graphical representation of eigenvalues.
Okay.
Yeah. So this little circle here means the number of factors. So that's factor 1, factor 2, factor 3, 4, 5, 6, 7, blah blah blah, until like usually like the eigenvalue. Script plot always show the number of your items. So for example, if you have 100 questions,
Yeah.
you're gonna draw like 100 like dots on this line.
And what do you call that? Like number 4? That's probably where we'd stop cutting them off.
Yeah. So pretty much like you're gonna here they're gonna put
What do you call that?
So this is like eigenvalue.
Yeah.
Mm-hmm.
So for example, if 1 here could be like 9. This one
Yeah.
could be like 8, 7, 6, 5, 4, 3, 2. Yeah. So this one could be 1. So if you find out that after you keep going for 5, the 5th factor, you're gonna be lower than eigenvalue of 1.
So you don't want to use it.
Yeah. So that means we're gonna decide to extract 4 factors from that set of questions.
I remember this.
Mm-hmm.
That's how we use the eigenvalue plus the script plot to determine the number of factors we should be extracted.
So we don't want to keep the factors that are below 1?
Yeah, so that means we stop here. So we're gonna keep only, so we know that from these set of questions, we're supposed to only have 4 factors or 4 dimensions.
Yeah, there's the Kaiser rule.
Yeah, that's why the eigenvalue needs to be bigger than 1. Okay, next one is the rotation. So after we determine how many factors we're going to be extracted, and then the rotation will help us to locate the items to their corresponding factors. That just extracted from the eigenvalue procedure.
Locate the items to
Yeah, or you can say loading items to the factors. You can say locate or loading because we call them factor loading. Loading items to the factors or to the corresponding factors. Yeah, that's what rotation does.
So it takes all the items and puts them on the 4 factors that you just...
Yes, exactly. So maybe for factor 1, we can have 10 questions. This one will have 5. This one will have number 5. This one will have number like maybe 7.
Okay,
Yeah.
that's cool.
So that's how they do the rotation. They assign the items into their most highly explained factors.
Yeah.
Telling you these 10 questions supposed to be explaining or talk about factor 1.
Okay.
So when we do the rotation, there's something that we need to know. First of all, you have to know orthogonal rotation, whether you're doing orthogonal rotation or you're doing oblique rotation.
Bleak.
Orthogonal means your factors, they are uncorrelated.
Uncorrelated.
Between your factors. So in our case, between these 4 factors, if they're uncorrelated, which means they don't have a correlation between each other, we're going to do a orthogonal rotation.
Yeah.
So if they're uncorrelated, then you choose an orthogonal.
Rotation, yeah, because rotation has a 2 method. And again, in factors, if they are correlated, you're going to do an oblate rotation. Yeah, remember, the correlation is between the factors, okay? It's not between items. And something you need to know that in SPSS, actually, orthogonal rotation is also called Verimax. That's one of the way to do orthogonal rotation. And that one is asked on the comps.
I remember that.
They're going to ask you, what is the orthogonal rotation? The answer should have Verimax.
Yep. So much knowledge to memorize.
There was another question on Dallenberg's exam that had a question about SPSS, the need for something. Where do you go to do something in SPSS's crosstabs?
Oh, that one's supposed to be under descriptive, but that's more like an SPSS question.
That's too. That won't be on the test.
Okay.
That's too heavy.
If you
Have
do
you-
SPSS, you will analyze descriptives, and you have a crosstabs there, and you
Crosstabs.
click that. That's how we do it.
Have you tried
That's
this
how you do it
comp
for
yet?
the chi-square.
Yeah.
Yeah. No, I have not. Have you?
No.
No.
Yep.
That's it.
Okay.
Yeah.
How many times have you done it?
Twice. It's hard.
I haven't taken comp yet.
Oh, it's hard. I mean, it's interesting stuff. I really liked it, but it's hard.
And yeah, and that's I think that's all for factor analysis. Do you have any further questions or additional inputs?
No, just the
Yeah,
one.
that's what Packet pretty much talked about. They didn't really go further beyond that.
I would just know the Kaiser rule.
What's the Kaiser rule? What is
Kaiser
it?
rule
that's
is used on
eigenvalue
the.
bigger than 1. That's
Yeah.
Kaiser rule.
The Kaiser is when you tell
yeah.
SPSS keep everything above 1.
Yeah.
Oh.
It's on page 76.
Yeah.
Yeah. That just means your eigenvalue needs to be bigger than 1.
Yeah.
Yeah. To get the most accurate extracted factors or dimension. You should
Yeah.
have.
Keep above 1.
Yep.
You can either use a screw plot, the Kaiser rule, or you can make it theory driven.
Oh. Now it's coming back to me.
Yeah.
So how do you choose your factors?
Yeah.
There's 3 ways
Yeah.
to choose
3
your
ways.
factors.
Yep. Kaiser rule, theory driven, or look at the screw plot, which is what Bongshi did with us.
Kaiser rule,
Job rule.
screw plot,
That's so weird.
or what? Theory?
Theory driven. You use theory to choose what you're going to keep.
Like the research and what you.
Yeah, but that one was not on the package, so
Yeah.
it's up
Good
to you
memory.
guys, yeah, to remember that.
No, theory driven's on the packet.
Where is it?
76. The bottom eigenvalues, bottom thingy.
Oh, square plot.
Yeah, Kaiser rule, screw plot, or theory.
Oh. Theory.
Theory. Zach.
I thought it's another word.
Oh, that's okay.
Okay, so, and actually the last analysis is item analysis, but again, it's like a very different, I want to keep it probably a little bit later because again, it's a little bit different set, so.
What's it called?
It's called item analysis and it's on page, under like the last sections. Yeah, because today's already 5, so we're just gonna leave it for tomorrow actually.
Oh, she's like, I want to go home.
No, I want you to go home.
We'll stay as long as you want us to stay.
I'm leaving.
See?
I love you guys' company, but I am so tired.
You see?
I'm so tired.
Yeah, it's like on, it's on page 96.
5:30.
Yeah.
196?
No, 96.
Oh.
There's no
I was
196.
gonna say, I don't have that packet.
Yeah, but that is actually, it's similar to fraction. It's more used when you're gonna develop your own psychometric tests. You need to do item analysis.
Oh yeah.
Yeah, so that's why it's gonna kind of very different than the regular, statistical analysis. Yeah, but at least factor analysis is actually, this one we always use it before SEM. Because the difference between PASS and SEM is SEM is like this. We call them latent, factors. Because remember in PASS analysis I use a square. Yeah, square means that you can measure that variable directly. But actually when you do SEM, each of these are your factors or dimensions. So which means each of them are gonna have
a bunch of loadings.
Yeah, like items. Yeah, so that's your item 1, item 2, item 3, item 4, item 5. So the same thing here. Yeah, so that's why it's a crazy model to do.
Wow.
Yeah.
So
this is SEM. So that's why in SEM we do a EFA, CFA, and then we do the structural equation modeling.
Wow.
Yeah, so factor analysis is also kind of like a priority analysis to do before you do the SEM.
So you can't measure the circles directly because
Yeah.
they're made up of all the
Exactly, from the items or questions.
the items.
Yeah.
So you can only measure the items.
Yeah, that's right. So that's why they call it SEM.
Is that like you can't measure depression, but you can measure the symptoms of depression?
Exactly.
Spatially,
Yeah.
right? Like ruminating.
Yeah, so PASS analysis, these variables, that's why they're like multiple regression. You can measure age, right? You can measure income. You don't have to do a factor analysis to measure them. You don't have questions. Yeah, you just measure them directly by numbers. Yeah, but in ICM, these are called latent factors.
Latent.
Yeah, latent means you cannot measure them directly.
Okay.
Cool.
Yeah, so that's just additional thing because after I talk about this, then you understand that.
Yes.
So that's why I didn't say it under the SEM section. Plus, they're not really talk about it in the packet. Yeah, they do mention the term latent factors, but now you understand why they call latent.
Yeah.
Because you cannot measure
them directly.
Yeah.
Yeah, that makes a lot of sense.
Alright. So yeah, so that's it. And so tomorrow, I hope we finish, decision tree, reliability, validity, and item analysis, and the last part of the test. So that's all left over on the packet. That should cover everything. Yeah.
Cool.
Okay.
Yeah,
Thank
I
you.
hope so we can finish everything
Oh.
tomorrow.
It's not that specific, but
Okay. So